Madam, your audio not connected. ఇప్పుడు ఓకే ఓకే ఓకే. ఎలా ఉన్నారు మేడం? అన్మ్యూట్ చేసుకోండి.
ఓకే.
ఎలా ఉన్నారు మేడం?
ఓకే సార్, బానే ఉన్నాను. మీరు ఫుల్ బిజీగా ఉన్నట్టున్నారు. అన్ని వెబినార్స్
ఏదో ఒకటి పెట్టేస్తున్నాను ఊరకొండకుండా. పేరు కూడా ఏంటంటే ఒక్కొరు ఒక రోజు వచ్చి అట్లా ఇంట్రొడ్యూస్ అయ్యి ఒక ఫోటో తీసుకున్నారు అనుకోండి, కోఆర్డినేటర్ ఉన్నారు కదా, ప్రొఫైల్ లో మీరు కూడా రాసుకోవచ్చు, ఫోటోలు పెట్టుకోవచ్చు అని. అది మేడం.
10కి వస్తారా సార్?
10కి వస్తానులే మేడం.
ఓకే సార్.
ఓకే 10కు వచ్చేసి ఎంత పని ఉంటే చూసుకోండి, ఇంకో 5 minutes టైం ఉంది.
ఓకే సార్, నో ప్రాబ్లం. హలో సార్.
ఎందుకు మేడం? అంటే ఈ రోజు ఇంకో లింక్ పెట్టాను కదా, మీరు గ్రూప్ లో చూడలేదా? మీరు
10 to 1.
Dr. Swamy, sir.
Sir, good morning, sir. Just now I make your co-host, sir. Good morning, welcome, sir.
Thank you, sir.
Srinivas Rao, sir.
Good morning, sir.
Sir, please wait 2 minutes, sir.
No problem.
People are joining till now. 22
Sure.
participants were joined.
We'll wait.
But 2-3 minutes, they will join. We will start, sir.
No problem. No problem. I'm
Okay.
ready.
Thank you, sir.
Dr. Munishami, good morning, sir.
Good morning, sir. Good morning. Welcome.
Thank you, sir. Thank you so much. Two days completed.
This is
Another
Thursday.
2 days are remains.
Yeah.
Okay.
Sir, can you see my screen?
Yes, sir. Yes, sir. It is visible, sir.
Visible, right?
Okay. Thank you, sir.
Shall we start, sir, or we can wait?
We will start, sir. 2 minutes. Madam, Geeta Sri, madam.
Sir.
Madam, please introduce, madam, our speaker.
Okay, sir. Okay.
Then the session will be start, madam. Okay, thank you, madam. Please introduce our speaker, madam.
Sir, is it visible, sir?
Yes, madam. Visible and audible also.
Visible.
Oh, okay, sir. Thank you very much.
Okay, ma'am.
Good morning to one and all. Just I want to introduce Mr. Srinivas Rao, sir. Srinivas Rao, sir, is a technology and management professional with more than 25 years of experience in the IT industry. He holds a master's degree in engineering from IIT Chennai and MBA from IIM Kozhikode. And he worked as reputed consulting and technology companies like PwC, Oracle, and PDP Australia. And his skill sets include IT consulting, system integration, design, and implementation of enterprise-wide applications. Sir is currently advisor to startup companies specializing in building data science, machine learning, and AI applications. And sir is currently involved into building ML and AL solutions for retail, energy, and oil and gas sectors. He also teaches data sciences, ML and AI from MBA students and engineering graduates. Sir regularly conducts workshops in data science, ML, and AI in engineering and MBA colleges, and consults students aspiring to get into the exciting and rewarding career in the data science. So it is great opportunity to me to introduce sir. Thanking you very much, sir. We are cordially invited to give for your lecture, sir. Thank you.
Thank you, Geetasri madam. Thank you very much for introducing the speaker today. So
Thank you,
now
sir.
I'm requesting the Srinivas sir to take up and welcome all the participants. I hope you will enjoy the correlation and regression analysis with our speaker Srinivas sir. Sir, please start, sir. It is now over to you, sir. Thank you. Thank you very much, sir.
Thank you, Munswamy, Dr. Munswamy, and thank you, ma'am, for the nice introduction. It's a pleasure for me to interact with so many faculty from across the country. So I also feel privileged that I've been invited by Dr. Munswamy to take up the session on statistics. Basically, I teach statistics as a part of the data science, machine learning, and AI course. I teach in some of the MBA colleges. I also teach in some engineering colleges. It's out of passion. That's why over the weekend and some online classes I keep taking. But otherwise, I work as an advisor to consulting to startup companies specializing in this field of data science, machine learning, and AI. I'm sure, sir, am I audible? No? Am I audible? Should I speak
Yes,
louder?
sir.
Or?
Yeah.
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 So basically, the subject of data science, machine learning, and artificial intelligence, picking up, you've heard if you open the papers or if you look at the news, this is a subject that has been hot in the industry. Be it you take any sector, you take government sector, you take corporate sector, IT sector, everywhere now companies are using machine learning AI for building a lot of applications, and this subject is agnostic to any particular field. You name it, health sector, you name it, retail sector, you take it manufacturing. So there is no field in the world today that is not being touched upon by this sector. So you can imagine the amount of importance that is being given to these particular subjects. And given that there are so many job opportunities, a lot of students, it can be students who are just passed out of their graduation, or even people who are working in the industry in different sectors, be it retail, be it health sector. Even doctors are also trying to learn this because this subject has got applications, a lot of applications, even in the medical field. Okay, so the medical field, in fact, is one of the largest users of data science, machine learning, and AI. And given that statistics is the foundation for learning these subjects, so learning statistics also becomes very important. So anybody aspiring to get into data science or learning machine learning and artificial intelligence, they need to have some knowledge of statistics, because we start using these concepts as we go along. So today I'll take up since this particular sessions for you is a sort of a short foundation course. I'll be taking up two topics. One is on correlations and the other is regression. I don't know the background of most of you, but I'm assuming that you are teaching in many colleges. Maybe some of you would have learned these concepts or maybe teach these concepts. I'm not very sure. But I hope that this particular session will be useful to you in some way or the other. How I'll approach this is I'll take you through the concepts first, and then I'll also try to take up some problems so that you understand the applications of this, and probably people who are already familiar with tools like Excel. Of course, there are a lot of statistical tools available in the market from different companies, and open source as well as proprietary tools. But to learn these concepts, initially statistical concepts, Excel is a good tool to start with. Okay. So many of you, since I'm assuming that many of you are familiar with Office 365, it can be Excel or Word or PowerPoint. You don't need PowerPoint or Word, but essentially Excel, if you are able to do Excel, you can learn many of these statistical concepts. Given that, what I'll do is, as I said, there are two topics I'll be covering today. One is on correlations and the other is regression. So I'll start with this topic on correlations. and then I'll run you through the concept, and then after that I'll solve some
Hello.
problems. Yeah, yeah, I can. Yeah. So if I'm not audible for some reason, just please tell me. Yeah. Now, coming to this topic of correlations, I'm sure you would have heard of this term in our day-to-day life. We normally talk of correlations between different phenomena that occur. For example, if the weather is hot, then it can mean that, example, in the context of a business, a weather is hot means that common sense also tells you that if the weather is, if the common sense also tells us that if the weather is hot, then the sales of certain products like ice creams and all these soft drinks will go up. And if the weather is cold, there are certain other types of products that might go up. So correlations can mean, for example,
Yeah.
yeah. So correlation means that basically it's a relation. So in the statistical concept, what it means is that how one variable influences the other. For example, as I said, temperature of in a particular place might influence the sales of ice cream, or temperature in a particular place might influence the sales of say winter clothing. For example, if the temperature, and suppose you go to colder places like say US and all, or some other countries where the temperature is cold, normally in winter season
Yes, sir. Yes.
the retailers who actually sell winter clothing, they expect that because the temperature goes down, the sales of winter clothing goes up. So there is a relation between two variables. So
Yes.
whenever there's some voice coming out, sir. I think if you are on mute now, and if you have a question, you can ask me, unmute yourself and ask me. Otherwise, I request you to put your this thing on mute. There's a mute button at the bottom when you can put your thing on mute, and then when you want to speak, you can unmute and then speak. So basically what we're saying is whenever there's a relation between two variables, then we mean there's a correlation. And in your previous classes, you would have heard of something called, when you learned about mean, median, mode, the measures of central tendency like mean, median, mode, you would have dealt with one single variable. For example, if you're trying to analyze one variable, it can be anything. So when you're trying to analyze one variable, there's some lines coming out. There are some lines coming out, sir. Okay.
Could I start? Yes, sir. Class.
Yeah.
Yes, sir. Lines are coming.
You're able to see some lines, is it, on my screen? I don't know. No. Muniswamy sir, you're able to see my screen properly, no? The slide?
Yes, sir. There are lines are there. Just go to the animate and clear the drawings actually.
Your screen is visible, but some lines are coming.
Somebody is drawing,
Please,
sir.
I'm requesting all the participants, please mute yourself. Unnecessarily you are unmuting and the disturbance is coming.
But I don't know, but suddenly the lines have come. I don't know. I didn't do anything.
Sir, hosts, sir, please. I'm requesting host to sir, mute all, sir.
I am muting all, but again they are unmuting and they are opening.
All the dear colleagues, don't do that. All colleagues, I'm requesting you don't do that.
Disturbances for us only.
There's an annotation also.
If you have any doubt, if you want any discuss with speaker, you can unmute. You can talk now. So even now also see people are like.
So at the bottom.
include ಮಾಡ್ಕೊಂಡ್ರೆ ಯಾವ್ದೋ ಒಂದು ಕ್ವೆಶ್ಚನ್ ಕೇಳೋ ಸಟ್ಟಿ ಏನ್ ಆನ್ಸರ್ ಆಗ್ಬಿಟ್ರೆ
Sir Srinivas sir, please unmute yourself, sir.
But somebody is muting me. I don't know.
Now I muted all.
Okay. Right. Got it, sir. Got it. So essentially, what I was speaking is, when there is a relation between two variables, then we say there's a correlation. Okay. Now, as you can see from that small graph on the right hand side of the screen. So whenever we talk of two variables, we normally call it as a bivariate analysis, because we are dealing with two variables. Now, one can be called as a dependent variable and the other is independent variable. One is the dependent is on the x-axis. Sorry, that's an independent is on the x-axis, and then the dependent is on the y-axis normally. So because it depends on the value of x. So as I said, when you talk of temperature versus the sales of ice creams, you can say temperature is the independent variable and then sales of ice cream can be the dependent variable, because the sales of ice cream depends on the independent variable, which is the temperature. So that's how we can relate to two variables. And when you say that there is a relation, there's a correlation. Okay, in the mathematical statistical concept, we say it's a correlation. That normally we are very familiar with the word called relation. You say that somebody is the father of certain child, or somebody is the uncle of certain person. So there you're trying to establish a relationship. But here in the statistical meaning, we are trying to establish a correlation between two variables, okay, two mathematical numbers. Now, why do we have to learn this so-called concept of correlation? Basically, correlation becomes very important in the context of, as I said, when you're trying to establish a relationship from a mathematical concept, you just cannot say there's a relation. Somebody will say how do you quantify that relation? That is when you try to come out with some mathematical formula which tells you some number which will indicate, okay, this is the amount of correlation. Otherwise, just saying that this variable is related to that, or some other variable is related to something else, will not make meaning when you want to compare. Okay, suppose I say temperature is related to sales of ice cream, or temperature is also related to sales of something else, then you want to compare and say, how is this different from that? That's when you have to quantify and work out some number which will tell you that, yeah, the strength of the relationship is this much. So I would say that the correlation between ice cream sales and the temperature of a day is much more than ice cream sales versus the sales of, say some other sales of televisions, for example. Okay, so, or sales of air conditioners or whatever. So that is how we establish correlation, and then we try to quantify it in terms of a number. And this also becomes important in the context. It's like just like you have learned mean, median, mode. This also becomes a foundation for a lot of mathematical model building, especially when we try to build the machine learning and AI models. This correlation becomes an important factor, because this is one of the first things that you do as a part of the exploratory data analysis. For example, if I say that a certain variable, for example, GDP of the country is dependent on say 10 or 15 or 100 variables, then the point is, if you take all those 100 variables and try to relate that to the GDP, then your model might become very complicated, or if the data is large, your computation time might also increase enormously. So in that case, what we normally do is we try to find out the correlations, and then we find that in the 100 variables, you might find that only 20 variables or 10 variables are trying to influence the GDP. In which case, you don't have to consider all the other 80 variables, just because they have some influence on the GDP. Okay, so what you try to do is you try to remove the variables which do not have any correlation with the dependent variable, in this case, which is the GDP. And then you say that, okay, because the correlation between that and the independent variable and the GDP is not much. For example, the traffic on the road and the sales of certain items, televisions, may not have a correlation at all. It might be very, very minimal. Okay. Now, so in that case, there's no point in tracking. If you want, a shopkeeper wants to estimate the sales of televisions in a showroom, he might compare it with for example, air conditioners can be related to temperature, but air conditioners cannot be related to the traffic that is, or the number of cars which are crossing a particular junction. There's no correlation at all. So that is how we try to eliminate some of the variables which do not have any influence on the variable that for which we are trying to model the particular equation. So that's where correlation becomes important, and then there's another associated variable which is called covariance. Basically, covariance indicates both are very much related in terms of the concept. But what covariance does is, while correlation gives you a number saying that the sales of air conditioners and the temperature is a number, say 0.9 or 0.8, we will see how you calculate that 0.9 or 0.8. Covariance only indicates how are the relations moving with respect to each other. For example, are they moving in the positive direction or they're moving in the negative direction? For example, I would say that the same example of temperature versus sales of air conditioners, are they moving together upward in the upward direction or in the downward direction? Downward direction means that if the temperature is going up, for example, common sense tells us that when the temperature goes up, the sales of sweaters will obviously come down, because they're inversely correlated. They don't move with each other. The correlation is very less. And then when you talk in terms of covariance, you will say that they move in the negative direction. Okay, because one increases, the sales of the other will reduce, so they move in the opposite direction. So that's how covariance and correlation have a relationship. But in terms of a number, correlation is a number. Both give numbers, but I'll tell you the difference when we actually go to the next slide, how the numbers are different from each other and why both of them are important. Now, when it comes to the statistical calculations, Covariance is, I'm sure you know of variables X and Y. In this case, we have taken a very simple example of variables X and variables Y. So when you take values like that, there is a very simple calculation. You take the mean of the variables X and then the mean of the variables Y, and then there's a formula for covariance. Statistically, we don't have to worry about how this is derived, but I'll also tell you when I show you the calculation that it's a very, very simple, intuitive to understand relationship formula, which you can easily interpret and then work out. And similarly, correlation, it is nothing but the covariance divided by the standard deviation. I'm sure you would have learned about mean, median, mode, and standard deviations in your previous sessions, or even in our +2, or even before that in our 10th standard, we also learned something about statistics where we learn about mean, median, mode, standard deviation, and variance, and statistical concepts like that. So correlation is nothing but you're trying to divide the covariance by the standard deviations. In other words, we are saying we are trying to normalize the covariance and coming out with some number, which is a value between -1 to +1. For example, the correlation value, when you find out mathematically, applying these formulas, you will always find that it varies between -1 to +1. It doesn't go beyond -1 or not does it go above +1. It only varies between -1 to +1. And the plus sign indicates that there's a positive relationship. For example, since probably you would have got some intuition now, the same example of temperature versus sales of air conditioners, when you actually do the correlation, you will find that it is some 0.85 or 0.9 or some value. But the sales of sweaters and the temperature goes up, the sales of sweaters will go down, which means that the correlation will be there. Maybe it is minus of say 0.65 or point whatever. There's a negative correlation. So the value will, once you see the value of correlation, you will actually figure out, okay, yes, there is a positive correlation or there's a negative correlation. But one important thing we have to remember is correlation and covariance, there's one term called causation. The term cause is an English word with which all of us are familiar, cause and effect relationship. So it means that just because you got a number, it doesn't mean that there is a cause of one variable is causing the other. For example, as I said, suppose traffic on a particular road and the sales of air conditioners, you might, when you try to draw the correlation, you might get a value of say 0.7 or 0.6, whatever, you will get some number. But that doesn't mean that the traffic is causing the sales of air conditioners. Okay, just because when you apply this formula and find out the value of correlation or the covariance, you get some number. For example, if you find out the value of correlation, you might get a value of 0.75. So just because you get 0.75, you cannot say that the traffic on the roads is influencing the sales of air conditioners. Okay, you might get a number, but that does not mean that this is causing the other. Okay, so that is where we have to be careful. Just because you get a number which is positive or negative in whatever sense, it doesn't mean that one is causing the other. So you have to understand that there is a difference between correlation and causation. Causation may or may not lead to a correlation, may or may not lead to a causation. A correlation between temperature and ice cream, there's a causation. Temperature is increasing, ice cream sales will increase. But in the case of traffic and the sales of air conditioners, you might get a number of correlation, but it doesn't mean that the traffic in the road is causing increased sales of air conditioners. So that is the main difference between correlation and that is the relationship between correlation and causation. So correlation and causation, as you would have figured out by now, basically establishing a relationship. And as I said, instead of just saying that one is related to the other, we cannot say that he's my uncle or she is my sister and things like that. Now then, when you talk in terms of mathematics, when you're talking in terms of variables, not only the relationship, but you also have to question as to what is the strength of the relationship. You have to quantify it. To quantify that, statisticians have come out with these equations and concepts. One is covariance and correlation. Covariance indicates whether the variables are moving together in whatever direction, and correlation, both will give a number, but correlation gives the main difference in terms of the number that you get when you find out the value of covariance and correlation is correlation, the number is always between -1 to +1. Whereas covariance, the number can be anything. When I show you the calculation, you will find that covariance number can be 100 or 200 or 1 million or 10 million. There's no limit to it. Okay. So when you, for example, you're trying to find out the covariance between heights and weights of people. For example, in a class of say 50 students, there are there in the class. Now, if you take the heights of these 50 students and the weights of these 50 students, you can find out that there are 50 weights, and for every student there's a weight. Suppose somebody's height is 5 feet 5 inches, his weight can be 65 kilos. Somebody's height can be 5 feet 9 inches, his weight can be 75 kilos. So like this, when you tabulate the entire thing, you have two variables. One is the height, the other is the weight. Now when you actually have this data and you find the covariance, then what you do is you apply this formula, you will get some number. Okay, you will get some number. But if somebody says that somebody will say that I will put the height in feet and weight in kilos. Somebody will say that I'll put the height in terms of meters. Okay, instead of writing 6 feet, he will write 1.8 meters. Okay, so everybody will have their own units, and then when you actually compute the covariance, you will find that the answer obtained by the person who uses feet is different from the answer obtained from the person who uses the meters. Or somebody can say that I'll put the weight in grams. Somebody will say that I'll put the weight in kilos. So when you change the units, then you will find that you get some numbers, and the number of the calculation done by one person might be different from the calculation done by another person. So that's the problem in covariance. But in the case of correlation, whatever units you take up, since you're dividing that by the standard deviation and normalizing it, you will find that let him take feet or meters, somebody can take kilograms or grams. Whatever be the unit, you will still get the same value of correlation, which is between -1 to +1. So that is how correlation standardizes the answers, standardizes the number, so that you can compare, you can do comparisons. Whereas covariance, you cannot do a comparison because the units will influence the value. Okay. But for example, if you're trying to find out the correlate covariance between two variables, suppose one of them is rupees, okay, the sales of some products. Now I can put the sales in terms of, say, suppose it is 1,55,325. I can put the entire number. Somebody will say 1.53 lakhs, okay, like that. Or if it is in crores, somebody will write the entire number. Somebody will write in terms of, suppose it is 120 crores, he will write 1,200 lakhs. Somebody will say that he will write in crores. Somebody will put the entire number 120 crores, 120 followed by 7 zeros. It's a big number. So when you put those numbers and find out the covariance, you will find that the values will change from person to person, because the type of the unit that they've taken is different. I can take rupees absolute, I can take lakhs, or I can take crores, and somebody will take millions. So depending on the unit, the value of covariance will change. But in the case of correlation, whatever be the units you take, you will find that the correlation values will remain the same, whatever be the units that you take. So that is the main difference between covariance and correlation. The other thing is covariance. Another confusing thing is covariance will have some units, whereas correlation, it's an absolute number. Between -1 to +1, there are no units. It's a standardized number that you get. So that is the main difference between correlation and covariance. Now, given the concept that I hope you understood the concept between the two. Now, to calculate these correlations, normally in statistics, there are several types of correlation that we learn, but the three main important correlations that are taught to people who learn statistics are Pearson's correlation. Then there's another thing called Spearman rank correlation. The third is the Kendall's rank correlation. There are three types of correlations that are most prominent. And each of them, then your question can be, why you should have 3 types or 4 types or 5 types? Because each of them has a certain application. For example, Pearson correlation, you will find that it is very much applicable in the case of continuous data. For example, when you say continuous data, it means that suppose the heights of people or weights of people, somebody can be 63 kilos, somebody can be 63.1 kilos, 63.2 kilos. That is a continuous data. And whereas in the case of the other two, as a Spearman rank correlation and the Kendall's rank correlation, you can use it for continuous data, but what you have to do is you have to convert that to ordinal data, which I'm not very sure whether you heard of this term called ordinal data. The word ordinal data comes from the word order, which means that in our day-to-day life, we also encounter ordinal data in terms of, for example, if I go to a showroom to buy shirt or my shoe size or my shoes. If I go to buy a shirt, the shopkeeper will show you sizes like small and medium, large, XL, double XL, and sizes like that. Okay. The same is the case with shoes. He'll say number 6 or number 7 or number 9 and things like that. So it doesn't mean that the shirt size are small. When you take two shirt sizes, for example, medium and large, you know that there's an order. You know that small is small, next comes the medium, next comes the large, next comes the XL and double XL. There's an order to it, but the order does not mean that it does not give you a relation. It doesn't mean that large is 2 times the size of small, or you cannot say the double XL is 3 times the size of small. Okay, there is no relationship. Okay, so there's an order to it, but that order cannot be numerically quantified in terms of a relation between the two types of numbers that you see there. For example, when you go to a restaurant, the restaurant fellow will ask you for a feedback. You, after having your food and all that, then he'll give you a feedback form. Then in that feedback form, they will be they ask you to rate them in a scale of 1 to 5. 1 can be highly unsatisfied, then you say satisfied, or then you say I'm satisfied, then or highly satisfied. You have some scale like that. So he'll ask you 1, 2, 3, 4, 5. Then you put, suppose you like the food, you say 4, or you don't like it, you say 2. Okay, that's a common thing, the common feedback form that you see in most of the restaurants, or it can be any other service. Even if you apply for a banking service, he gives you a form to fill it up. But there, suppose you give a satisfaction for a score of 4, and somebody gives a satisfaction rating of 2. It doesn't mean that the person who gave 4 is 2 times more satisfied than the person who gave 2. There's no relationship. There's an order to it, but there's no relation between them. So that is that type of data where there's an order, but there's no relation. You cannot quantify that in one variable in terms of the other. Just like weight, and for example, weight. Somebody is 60 kilos and somebody is 30 kilos. You can say that this person is twice the weight of the other person. Or somebody, you can also say that one person is half the weight of the other person. Similarly, the case with height, or similarly the case of salary. Somebody's salary is 2 lakhs, somebody's salary is 1 lakh. You can say that this person's salary is twice the salary of the other person. But in the case of ordinal data, you cannot establish that relationship. You can only say that it's an order. It's an order. For example, designations in companies. For example, assistant professor or associate professor and professor and a dean, for example, there's an order to it. There's an order to it. But you cannot say a dean is twice as powerful as a professor, or a principal is, or vice chancellor is twice as powerful as a professor. You cannot quantify a relationship, but you can make out there's an order to it. So that type of data is called an ordinal data. And for ordinal data, you can use this Pearson correlation, which is the first one. You cannot use for that, but you can use it. In such type of data, you can use the Spearman rank correlation or the Kendall's rank correlation. And they have, as you know, in mathematics, everything is expressed in terms of some number or some symbol, like sigma is for sum and pi is for multiplication. So Pearson's correlation, you have R, which is the variable denoted for that, and this is the Spearman rank correlation, it is rho. And for the Kendall's rank, it is tau, okay, the Greek letters. So this is the notation used for these 3 correlations. And then applicability, I said one is for continuous data, the others are for ordinal data. And when I said continuous for Spearman and Kendall's, I put both. Reason is you have to convert. For example, when you apply Spearman rank correlation, you have to convert the continuous to ordinal, then apply it. You cannot apply it as it is. So that's the reason I put that as a slash. Okay. Now, coming to, before we go into the Excel sheet, I'll also show you how these calculations are done in the Excel sheet. Before that, I just want to show you how the background, the concept behind that, and then we will move to the Excel sheet where I'll show you the detailed workings. And then if you have a obviously you're in front of the computer, people who are accessing the computer, if you are familiar with Excel, you can also do these exercises in parallel, or you can do it later on. Now, as I said, the Pearson correlation is one method for finding out the value of the correlation. So Pearson is one mathematician who has done that. So Pearson's are, how do you find it out? There's a formula for it. Okay, there's a formula. I just show you the formula. It's not a very complicated formula. It's very intuitively understandable. Now, when you apply that formula between 2 variables x and y, then you get a number. As I said, this correlation is between these correlations are between -1 to +1. That's a standard. So when you find out the value of Pearson's correlation R, then you get a value between 1 to -1 to +1. So based on that value, you can interpret how the data is related. For example, if you can see on this graph, there are 6 graphs plotted, for example, and one is a line. Suppose the first line you say is R is 0.7. So when you do this, apply this correlation formula and find out the value of R, you get a line like this, and you get a number. Okay, that value of R, which is 0.7. Similarly, when you take the second graph, you get a value of R is equal to 0.3. Similarly, when you take the third one, you get a value of R is equal to 0, which means the line is perfectly. And remember, in all these correlations now, the main thing that is important is the linear relationship. You're trying to establish the linear relationship. It is not any other type of relationship, but the linear relationship. That's very, very important. For example, people who are familiar with mathematics and all that, you would have known about parabolas or circles and all that. Even suppose if you take the equation of a parabola, which is y is equal to ax square, okay, whatever, or you take an equation of an ellipse or whatever, any other mathematical model like an ellipse or a parabola or things like that. For example, an ellipse or a parabola will be y is equal to ax square. Now, when you put a value of x in that as 1, you get value of y as, suppose a value is 5. When you put a value of x as 1, you get y is equal to 5. Similarly, when you put a value of x as 2, it is 5 into 2 square, which is 20. So you can argue that there is a relationship between y and x because you are putting a value of x and you're getting a value of y. Then you can say, how come that is not correlation? It is not correlation. It cannot be solved using these methods because all your correlation methods can only establish the strength of the linear relationship. If there is a linear relationship, then you can find out the values. If it is some other type, then you cannot use these particular methods for establishing the correlation. So you can see from these figures that one value in the first on the upper side, on the upper part, there are 3 graphs. One is r is equal to 0.7, r is equal to 0.3, and r is equal to 0. And from the bottom ones, you can see r is equal to minus 0.7, r is equal to minus 0.3, and r is equal to 0 again. So I've just taken some examples for you to understand. As I said, the value of the correlation is always between minus 1 plus 1. As you can see, all these values, they are between minus 1 to plus 1. Okay, it ranges from minus 0.7 in one case, it goes up to 0.7 in the other case. So it is always between minus 1 to plus 1. That is how you get the value. The other thing is, if the line is sloping upward, you get a positive value. Yeah. Pardon, any question you can ask me. Yeah. Yeah. Hello. Yeah. So if the line is sloping upward, if you observe the figures, the 6 figures that I put up on the slide, you will understand. By now you would have got an intuition of how what the numbers mean. For example, you can find that when the R value is positive, the line is sloping upward. If the R value is negative, the line is sloping down. That's one thing. And then when you find that the line is able to, when the points are closer and then the line is able to fit it properly, you get a higher R value. You take the case of r is equal to 0, where the points are all scattered around. So when you do a correlation between them, you find that the r value is 0 because there is no linear relationship at all. You cannot establish a relationship. Okay. Similarly, the case of bottom, you will find that the slopes are going down, which means that there's a negative relationship. The case of the sales of sweaters going down when the temperature goes up. Okay, that's a case of a negative correlation. So like this, intuitively, you can think of so many examples in your day-to-day life. For example, years of experience and salary. There is if you would have realized that when you plot years of experience on the x-axis and the salary of a person on the y-axis, then you will find that it's a line which slopes upward. Okay, it's a line which slopes upward because as the experience of a person increases, then the salary increases. Assuming normally that happens in the government and private sector, you cannot say. But if you plot the salaries of people on the x-axis in the government, people working in the government sector, and the salaries on the y-axis, you find that the line slopes upward, and you can find a correlation. Okay, that's how you can do it. And obviously, when the correlation is high, then you say that okay, as age increases, the salaries are increasing. And for example, in some companies, after a certain age, the salaries might stagnate. In which case, the line will go down, and then you say the correlation is lesser. As age increases, it doesn't mean that the salary increases as high as proportional as it was in the. That's how you can interpret the values of correlation. So that's how the formula of Pearson correlation can be applied. So this is the formula which is used for Pearson's correlation. When I show you the calculation, you can understand the formula more in detail. And what has to be kept in mind, as I said, is there are 3 things to be kept in mind. One is the correlation may not indicate a causal relation. It doesn't mean that, as I said, traffic, if you draw a correlation between, suppose you find the value of Pearson's correlation between traffic on a particular and the sale of air conditioners, okay, whatever, you take any example. And then you find that you might get some number, but it doesn't mean that just because you got a number of correlation of say 0.65 or 0.75, it doesn't mean that this is causing that. Okay, there's no relation. Okay, there can be a relation. There cannot be a relation. So correlation value does not mean that there is a causal relation. That's one thing. Okay, then similarly, if you take the other side, just because there's a causation doesn't mean there'll be a correlation. So like this, it can be vice versa. And the other thing which is also important is correlations are very sensitive to outliers. I don't know whether you heard of this term called outlier. Outlier is something which is not in the normal. For example, when you're tabulating the marks of students in a class, and then you tabulate them as it is, and then suppose by mistake, if somebody's mark, instead of entering it as 85, somebody put it as 850, okay, by mistake, then you find that the correlation values will differ a lot, okay, differ a lot. If you put them in the, so outliers are numbers. For example, if by instead of 85 by mistake somebody puts minus 85, then the correlation get influenced a lot, okay. So correlations are very, very sensitive to outliers. And then, so that's for example the same case of age versus salaries of people, of employees. If somebody's salary is very, very high, for example, if somebody is age say 45 and he gets a salary of say 1.5 lakhs, and if somebody is 45 years and he gets 1 crore, okay, that's an outlier, which there might be very few people who get that salary, okay. And then that usually happens in the private sector, where the same age group, you will find that some people get very high salaries, especially in the IT industry. That's when the outliers will cause a shift in the correlation. So so they get greatly influenced by outliers. So that's another thing that has to be kept in mind. Right. Now having explained correlation, and especially the Pearson correlation, I'll take you through a small Excel sheet where I'll show you how these correlations are calculated. I'm sure people who are familiar with Excel, they will understand it very easily. People who are not familiar also, it's not rocket science. It can be learned very easily. You can learn Excel within a day or two. It's as simple as that. So I'll give the example of are you able to see my screen, all of you, the Excel sheet? Dr. Munswamy, you can see my sheet.
Yes, sir, it is visible, sir.
So I'll solve some problems now. Given that the theory part, I've covered the theory part, especially of Pearson correlation, I'll take up a small problem so that you understand the calculation behind it, and the different variables that influence the correlation. Here I've taken a very simple example: the temperature of in a place on different days, and the sales of Coke, for example. So temperature is 27 degrees centigrade, and then the sales of Coke on a particular day is what 10 million, say 10 million cases of Coke or whatever, so, or 10,000 cases of Coke. So like that, they have tabulated the temperature and the sales of Coke on different days. The temperatures you can see. Now, if you want to find the correlation between these two, that is, I've highlighted just for your understanding, temperature and sales of Coke. I want to find out the correlation. So in this Excel sheet, I've done two things. I have used the formula which you find in statistics books, the one devised by the statisticians. But Excel also gives you a very simple way of calculating the correlation. So what I'll first do is I will solve the same problem using the statistical formula that I showed you in the slide. For example, the formula says that it's a very simple formula intuitively. We should not, I request you not to memorize. You don't have to memorize the formula. You just have to think of the logic behind it, and you will not forget it for the rest of your life. For example, when you have temperature values in your yesterday's class or whatever, you would have learned about mean. Okay, mean is nothing but the average. So you have the temperature is recorded on some number of days. The total temperature, when you find out the total and divide by the number, you will get the value of the mean. So mean value is nothing but the sum divided by, for example, if you are trying to find out the mean of, say, the marks obtained in economics in a particular class. Suppose you have 100 students in the class. What you do is you add up the marks obtained by all the students and divide by the number. 100 students, you get the mean. As simple as that. Now, similarly, I found out the mean, which is nothing but the average. So Excel has a formula which is average. You just have to find the average. When you enter average is equal to average and highlight the cells, it automatically gives you the mean value. Okay, you got the mean value. Similarly, I found out the value of the mean for the sales of Coke. Just average of the values of the cell, and then I got the value of mean as 14.9 for temperature for sales of Coke, and for temperature is 36.7. Okay, now, and the count of the number of, there are 15 days during which the readings have been taken, and so this is the data. What I've highlighted in now, that is the data that is given to us. That's all. These two variables, now you can call temperature as the x variable, and then you can call the sales of Coke as a Y variable. Okay, whatever you can call it, A or B or X or Y, doesn't matter. Now, what I do is from each of these values, I subtract the mean. So X, so when I subtract the mean from each of these values, 27 minus, I got a mean of 36.7. So from each of these values, I subtract the mean, I get a value. So like this, for each value, I subtract the mean, I get some numbers. Okay. So what I get is X from each value of temperature, I'm subtracting the value of the mean of temperature for all the 15 days. Okay. I hope you got it now. From each value of the temperature, for every day's temperature, I subtracted the value of the mean for these 15 days. You have 100 records, you find out for all the 100 records a mean. And for each record, for each day, you subtract the mean from the given value. So I got these values. Similarly, for the Y variable, which is the sales of Coke, I subtract the value of the mean from each of these variables. I get a number like this. Okay. So you can see that the headings are X minus X mean and Y minus Y mean. So these two are the values that are computed. Okay, these are not given to us. As I said, the values given to us are only the temperature and the sales of Coke, which I've highlighted. Okay, the others are all what we are computing right now. Then what we do is you are multiplying these two values, the values that you just computed, X minus X mean and Y minus Y mean, or in mathematical statistical notation, you say X minus X bar or Y minus Y bar. Which, and so 47 that you see here is just a multiplication of these two values that you just computed, that is the X minus X bar and the Y minus Y bar. And the next thing is and you multiply both of them, X minus X bar into Y minus Y bar, which is this thing. And then you find out the square of the first value, which is X minus X bar whole square. You get a number, you square of this. And then essentially for the Y minus Y bar, you get a square of this value. Okay, then when you find it out and sum them up, you get these numbers at the bottom. So, and in the formula, the Pearson's correlation, which I showed you, it is nothing but the product of these two values, X minus X bar into Y minus Y bar. So how do you get X minus X bar and Y minus Y bar? From each value of X, you subtracted the value of the mean, you get X minus X bar. And from each value of Y, you subtracted the value of the mean, you got Y minus Y bar. You multiplied them, you got, and you sum them up, you got the numerator value here. So this numerator, and what is the denominator? It is nothing but X minus X bar whole square and the X minus Y bar whole square, and then you get the value of the Pearson's correlation, this 0.932. I just divided the numerator divided by the square root of these two denominators, multiplication of these two denominators, and then I got the value of Pearson correlation. So 0.932 is the value of correlation. So I just showed you how, given that you have two variables X and Y, how you can compute the value of Pearson correlation by doing all these calculations of X minus X bar, Y minus Y bar, multiplying them, and then finding out the square of X minus X bar whole square, Y minus Y bar whole square, summing them up, and then you get three numbers. So on the three numbers, one is the numerator, the other two are the denominators. You divide the numerator by the square roots of the denominators, so you get the value of 0.932. So that is the formula which you apply. And so in our olden days, when we didn't have computers and all that, all these students were doing it this way. They're finding out the values, multiplying them, and dividing all this, you get a value of 0.932. Now the same number, I've done the same thing in Excel. How do we do it is the same value. I just have to use the formula correl, C-O-R-R-E-L, which is the formula for correlation, C-O-R-R-E-L. Then I define the first variable, which is X, these values of the temperature, comma, the values of the sales of Coke, this value, and then multiply and close the bracket and close the bracket and say, I select these values of sales of Coke. Yeah, I select the values of the sales of Coke and then press. I got the value of 0.932. Okay, the same thing in Excel. People who are familiar with Excel, they would know this. But this is how the same computation I've done by doing all these calculations and getting the value of 0.932 by one simple formula, correl, C-O-R-R-E-L, and selecting these two columns. We call them arrays. We call them the columns here. In this case, temperature as one set. B3 to B17 is the values of the temperature. And similarly, C3 to C17 are the values of the sales of this particular product Coke. And then you get the value of the correlation. So this I've computed by applying the formula in Excel. So like this, Excel gives you so many formulas for finding out all your statistical. It does. It has a lot of functions to do all your statistical calculations. Okay. Now coming to the other one now. So since we know that now, what does this point 932 tell you? The point 932 tells us that now, as I said, correlation is always between -1 to +1. That is the first thing that we learned, -1 to +1. So this is the range of correlation between -1 to +1. Okay. Now -1 -1 to +1. So this is the range of correlation that we learned. Now you got a value of 0.932, and you could make out that it is between -1 to +1. Okay, that is so. It is correct. Now this 0.932 tells us what, as we have seen in the slide before, we have seen that if the correlation, you have seen these figures before, you see that if the correlation is high, then there's a good linear relationship between the two variables. In this case, it is the temperature and the sales of coke. So the same thing you can see in the Excel sheet. 0.932 is a high value because 1 is the highest value. You got a value of plus 0.932, which is a high value, indicating that there is a good correlation between the temperature and the sales of coke. Commonsensically also, we know that whenever the temperature in the city or in the place is high, the sales of soft drinks and these beverages will go up. Okay. Now, coming to the other one. Now, this is a case. The second value I found out for the sales of temperature and the sales of sweaters in a particular place. Now, obviously, you would have realized that when the temperature is more, the sales of sweaters will go down. So I've computed the value of correlation for this particular case, where between temperature and the sales of sweaters, when I applied the formula Correl, CORREL, and selected these two variables arrays, that is temperature and then the sweaters, I got a value of 0.968. So it shows that the value of 968 is high, which means that the sales of temperature is greatly influencing the sales of sweaters, which commonsensically also we know. And the other thing is, the value is between -1 to +1, -0.968. Now you realize that it is within the expected range of -1 to +1. As I said, correlation value can never go below -1, or it can never go above +1. So you got these two values of correlation, 932 and -968. One is for the sales of coke and the temperature, and the other is for sales of sweaters and temperature. So this is how you apply the Excel formula to find out the correlation. Like this, you can apply for any. It's simple. All you have to do is select the two variables and then apply the formula, and then you will get the. But concept-wise, you should understand how this is done or how this is calculated. That is the reason I wanted to show you how, without Excel formula of Corel, how do you actually calculate. I've done it by the old statistical way of calculating each of them, adding them up and dividing one by the other. You get the value of 0.932. And I showed you the same thing, how you can arrive by just finding out or just applying this formula and getting the value of the correlations. As simple as that. Now, I also told you, if you remember, I also told you that the outliers can greatly influence the value of correlation. Now, as I said, when you are tabulating the marks of your students, and then instead of 85 marks, somebody by mistake he puts it as 850, or by mistake somebody enters a minus sign and puts it as -85. Okay. So suppose you're trying to find out the correlation between students of one section and students of another section. For example, there are two sections in a class in a college, and in section A, you tabulate all the marks obtained by students in the economics subject, and tabulate the marks obtained in economics in the other section. And you suppose you're trying to find out the correlation. Now, if by mistake in one of the classes somebody by mistake enters wrong numbers, instead of 75 they put 750, or instead of 75 they put -75, some wrong numbers like that, then what will happen to the correlation is something. So these numbers are outliers which don't belong to the expected range of values. They are all called outliers. For example, as I said, in a company where there are, say, 1,000 people or 10,000 people working, there would be many people in the salary bracket of say 50,000 rupees a month to say 2 lakhs or 3 lakhs a month. But if somebody is drawing say 20 lakhs a month or 50 lakhs a month, they are outliers. Okay, they are outliers. So how will these outliers actually influence the correlation is something that we have to understand. Okay, now I've taken the same example, same data, but the same data in this case, I've highlighted one particular value of +15 here. Okay, +15 here. This +15. Now you will see how, by making a small mistake, okay, by creating an outlier, the correlation is getting influenced. For example, instead of plus 15, by mistake, the person has made a wrong data entry of minus 15. So the same data, when you find out the correlation, see how the correlation has changed from a value of 0.932 when the numbers were correct. When you entered one wrong number by mistake, minus 15, the same 15 became minus 15. The correlation drastically went down to plus 0.267. See how the outlier is influencing the value of the correlation. Okay, that is another important concept that you have to remember. How correlation concept, how it is calculated, from the formula as well as from the Excel formula. Thirdly, how is the correlation? You also learned that correlation does not mean causation. Okay, correlation does not mean causation. There might be a cause effect, there may not be a cause effect. The third important thing is outliers. So if there are outliers in the data, then they can lead to mislead the person into thinking that yes, there is a correlation between the two variables, and I can go ahead, because business decisions can be taken based on certain interpretations, and suppose there are outliers in the data and then you don't take care of them by removing them or whatever. What happens is can lead to wrong interpretations. Okay, that is an important thing that we have to remember. That's one thing. And the other thing that I also told you about is about the causation. This is another example of causation. Here, as you can see, I've taken some values. The y is equal to x square is a very common equation is the equation of a parabola. People who are familiar with mathematics, they will understand y is equal to x square is an equation of a parabola. So whenever you put a value of x, you get a value of y. You just plug in the value of x, you get a value of y. Now, when I've taken some values like minus 10 or these numbers, I've taken about 20 numbers, and then I found the value of y by y is equal to x square. Okay, just the simple formula. And then when I plotted them on Excel, I got this parabola. As expected, I got this parabola. So, and I applied the correlation, the same formula, the Pearson formula correlation, which I've applied earlier and got these 0.932 and this minus 968. I got a value of correlation as 0. Okay. So what does this indicate? Now, if you ask me, then you can ask me, when there is a relationship between y and x, you are saying that x, you put a value of x, you are getting a value of y, which means there is a relation. But why are we getting a value of correlation as 0? We got 0. Okay. So why are they conflicting? As I said, correlation value does not indicate two things. Correlation indicates the strength of a linear relationship. It's a linear relationship, it's not a curvilinear or normal relationship, linear relationship. Here you can see that there's no linear relation. It's a curvilinear relation. That is the reason why you are getting a value of 0, or maybe you get a value of close to 0.1 or 0.12 or things like that. But if there's a straight line, it is the correlation. Whenever you mean correlation, it is the strength of the linear relationship. It is not a if there's an if you can fit a curve or something like that, then you cannot apply correlation. Okay, so that is the reason why in this case, though there is a relationship between y and x in the form of y is equal to x square, you still got a value of correlation as 0 because there is no linear relationship. So these are the important concepts that I wanted to make you understand based on the calculations that I've done in the Excel sheet. Right, that is one thing. Then apart from this, there is another important, I am assuming that yesterday you have learned mean, median, mode and the other statistical concepts. And now today we will be learning about correlation and regression. So now, as a summary of that, here's an important data that probably I thought you would be interested in. There was a French mathematician called Anscombe. So he came out with 4 sets of data. As you can see on my screen, there are 4 sets of data, 1, 2, 3, and 4. Okay. Now, this sets of data, when you find out the value of the sum, then the average, which is the mean, the standard deviation, and the correlation. Now today you have learned correlation. So yesterday you would have learned about mean and standard deviation and things like that, and today about correlation. So surprisingly, he came out with this 4 sets of data where the sum is same, okay, for the x values and the y values. The average is same for x values and y, the average is same for all the 4 sets. So you'll see that it is 99 for the x values, it is 99 for this data set, it is 99 for this data set, it is 99 for this data set. Similarly, average is 9 for all the data sets, and standard deviation is same for all the data sets. Similarly, for the y variable also, these values are same numbers, there is no difference at all. And the other thing is the correlation also is the same for all the numbers. The number sets are different, but correlations are all different. Okay, the correlations are all the same. But what does it indicate? What does it indicate? It doesn't indicate, because it's a very interesting paradox, because there are 4 sets of data, and then for all the sets of data you got the same values of the sum, the average, the standard deviation, correlation. Okay. Now, but if you look at, if you give these 4 data sets to the people, they'll say it's the same because you're getting the values the same. But do they mean that they can you lead to the same interpretation? No, because when you actually plot them on the graph, on the x and the y axis, you'll find that the graphs look different. Okay, one graph is like a scatter plot, plots points up and down. Here you can see that the graph is a curve. Here you can see that there are almost in a line, and then one point is slightly above. And the other things, this particular data set, you'll see that all the points are in one line. There's only one point which is an outlier, but the data, the summary statistics, the sum, average, standard deviation, correlation are all the same. Okay, so this leads us to an important conclusion that all these statistical parameters, no, you cannot go blindly by the numbers that you get. So that's where the concept of visualization also becomes important. Whenever you work on statistical concepts, visualization, like drawing graphs and charts, becomes important, because what you cannot see in numbers, you can see when you do the visualization in terms of drawing the histograms or the bar charts or the line chart. There are several hundreds of charts available today. In fact, you have special packages like Tableau and Power BI, and there are a lot of ClickView, a lot of packages which have come, which are used widely in the industry, where they have very good visualization tools where you can actually interpret data in several forms. They can be radar plots and bar charts, whatnot. There are hundreds and hundreds of forms of in fact, there's a whole industry running behind it. I don't know whether you heard of this product called Tableau and Microsoft Power BI. So they are one of the highest paid jobs in the industry today. The visualization people who do visualization, they are one of the highly paid guys in the industry today. So that's the power of visualization. So statistical numbers, first of all, as you move from data to statistical computations like mean, median, mode, and other things, you are getting to some form of refinement where you are able to summarize the data and understand. For example, when you find out, when somebody asks you what is the value of the average mark obtained in economics in a class, you will say that the average is about 55. Somebody will say that in other section, somebody will say the average is 75. So this number of average or whatever gives you some indication of where the students lie as a whole. Okay, if there are 100 students in the class, I give you all the 100 numbers, then you get confused. You will not be able to figure out what has been the distribution. But if I say that the average is 65, or then you say the standard deviation is 5, then that gives you an indication of where the students on an average lie. And standard deviation, as you would have learned, it gives you the spread of data. See, many people get 10 or 15 or 20, and people get 80 or 90. The standard deviation is high. If everybody gets say 55 marks, 56 marks, 54 marks, all the 100 people get between this range of 54, 55, 56 or 60, then the standard deviation value comes very low. It can be 2 or 3 or 4. It's a low standard deviation. So while the summary statistics of mean, median, mode, they give you the measure of central tendency. The standard deviation variance, they give the indication of the spread of the data. Correlation gives you the relationship between the data. Then visualization gives you something more than that. Though you have all these variables in place, still it is able to make you see something that you cannot see from these numbers. Okay, that's how visualization becomes an important topic to be learned in statistics. Okay, that is the other one. Now, having learned, sir, Munish, am I going fast or slow, or is it okay? Or it's up to you.
It's okay, sir. No problem.
Okay. Are you able to understand, sir?
Yes, sir. Okay, sir.
Okay. Yeah. So next thing is something called so we have learned about the Pearson correlation, where we understand that it is used normally for the continuous variables, right? Now, pardon me?
Yeah.
Some resound is coming, ma'am. Ma'am, you're trying to ask me a question. Is there any? Yeah. Okay. So here, Pearson's correlation. Pardon me? Not able to hear you, ma'am.
Hello, Nageshwar Rao. You are unmuting. B. Nageshwar Rao. Okay, we are unmuting. You have any doubt, please ask me. Otherwise, you are I'm meeting you and but you are unmuting. This is creating some disturbances for all. Okay, sir. Continue, sir, please.
Yeah. So the next correlation coefficient we learned today is on Spearman correlation. Okay, Spearman correlation, as I said, it's called a rank correlation. I'll explain what is rank in a short while, and it is used for, as I said, these different types of correlations have been quotients have been invented by statisticians because one thing cannot fit all the types of data. See, you have learned about mean, median, mode, and all that. It is not. Why did statisticians stop? Why did they not stop with mean? Because they found that mean is not satisfying some criteria. They invented median, then mode. Like this, they came out with several statistical measures to interpret data. Similarly, the Pearson correlation is used for continuous data. We have seen how it can be used. Then we also now we get into something called Spearman's correlation coefficient, which is mainly used for data. It's called a rank correlation because it is used for values that are ranked in some order. That's the thing. Now there is again like that. There's a formula. We will see how this formula is applied to get the rank, the Spearman correlation coefficient, and more importantly, it indicates there's one important term in statistics that we have to learn. It's called a monotonic relationship. Monotonic relationship. Basically, a monotonic relationship is like this. For example, when you say there's a monotonic relationship, it means that if one of the variables is increasing, the other is also increasing. Okay, it also increases. Okay, it can also reduce. Uh, uh, but what happens is when if the function reduces and increases, there is like a cyclical manner. Okay, like a cyclical manner. Then it is not a monotonic relationship. For example, if you plot the age of people versus the salary, you might find that the graph it may not be a straight line, but it can be it can be a sort of a curve or a curved line which goes up and up and up. And similarly, when you try to draw the curve for the graph for temperature and sales of coke, it's a graph that goes up. The sales of sweaters versus the temperature, it's a graph that goes down. And for example, if you are trying to plot the temperature variation in a particular day, for example, in a particular day, you will find that in the morning, suppose you take today, temperature in Hyderabad would have been, say, in the morning, probably it is around 18 degrees centigrade or 20 degrees centigrade. And as the sun rises and then as by 10 or 11 or 12 or 2, what happens is the curve keeps going up. Okay, from maybe in the morning it is 20 degrees centigrade, then as you go up to say afternoon 2 or 3, it might go up to say 34 or 32 degrees centigrade, goes up. And after that, maybe from around 4 it keeps going down again. From 32 it goes down to 30, like that, and again in the evening it goes down. It follows its cycle, some cycle it follows. So whenever there's an up and down movement in the variable, then it is not monotonic. Okay, a monotonic relationship, you call something a monotonic relationship when the variable keeps on increasing. Okay, it may not increase like a straight line, but it keeps on increasing in some manner. Okay, but or it can also reduce in some manner. But as I said, like temperature in a day, it cannot keep going down and up and down in a cyclical manner. That's not a monotonic relationship. So this Spearman correlation quotient, it gives you a value between -1 to +1, like the other Pearson correlation, but it also gives you the strength and direct monotonic relationship which exists between two variables. Okay, that is the difference. Then we will also see how is it different from the Pearson correlation in a short while. Now, when you compare in this slide, basically you can see that there are some graphs. Now, I have shown you the difference between the value of the Pearson correlation and the Spearman correlation for each of these cases. Okay. Now, look at the first graph. In the first graph, it's a perfect straight line. The line is up, as you would have expected for a perfect straight line going up. Okay, there are no points up and down. They're all falling in the line. Then the correlation value is +1 because it's going up. Suppose it is going down, it will be -1. Okay, and the values are same. Then, if you look at the second graph from the left, you see the Pearson correlation 0.851, but the Spearman is +1. Pearson correlation, why is it giving a value of 0.851, not +1? Because Pearson correlation, as you would have seen, it finds out the difference between the x values and the mean, the y values of the mean, as you would have seen in that calculation we have done. And then when it computes x minus x bar into y minus y bar, there is some value that you get values, when you divide, you will not get a perfect one. Okay, but Spearman correlation, when you do it, you get a plus one in this, which indicates that the values, the relationship, there is a relationship and it is rising. It only tells you that it is rising. Okay, and when it is rising, it gives you a value. Okay, in this case, it's a perfect one. It is rising. If you take the third graph from the left hand side, the Pearson's is and the Spearman, they are almost giving the same value, 0.093 minus 0.093. And if you take the next one, the fourth one from the left, it is going down. So it is Pearson -1. That is one case. And then if you look at the last one, the Pearson is minus 0.799. The Spearman is -1. So this would have given you an indication that whenever the relationship is an upward trend or a downward trend, Pearson might give a higher value, but no, sorry, the Spearman will give a higher value. The Pearson, it depends on the because it computes for every value of from every value of x, it subtracts the mean value and does the computations. You'll find that it will normally never be equal to 1, okay, unless it's on the straight line. But Pearson, but Spearman, what it does is, by looking at the graph, you can say that, okay, Pearson, the Spearman is going to give a higher value because it only gives an upward trend or a downward trend, and the strength of the relationship in terms of the number. So that is the main difference between the Pearson's and the Spearman correlation. And the method of computation is also slightly different. I'll show you in a short while how the value of the Spearman correlation is calculated. And comparison, see, if you look at this graph also, the other thing is in the Pearson correlation, we have seen when outliers, how they're affecting the value of the Pearson's correlation. I showed you how that when the temperature of on a day from plus 15 degrees centigrade, somebody has made a mistake and put minus 15. You've seen that the correlation came down from 0.93 to it came down to 0.267. So I told you how I also gave the example of salaries of employees, where if somebody gets a salary of 1 crore, how does it affect the correlation? It's an outlier which affects the correlation, but Spearman correlation, it is not much affected by the outlier. That's one important thing. And if you look at this graph, for example, on the right hand side, if you look at the graph, it is a relationship between the number of the hours of past and the number of, there's some other variable, and bacteria, I think, yeah, bacteria in a biological study. So the hours have passed and the bacteria is this shows how much the bacteria has multiplied over a period of time. Okay, initially with the passage of hours, no, the bacteria has not multiplied much, but after a certain time, the bacteria started multiplying in a very exponentially. So you will find that it is flat for a long time. After that, it grows up exponentially. And if you find the value of the Pearson correlation for this graph, it is 0.58. But Spearman correlation, see, it is 1.0. It is a perfect one, because Pearson looks at whether the graph is rising or it is falling. Okay, based on that, it gives. But Pearson, what it does is it computes these values, and then it finds that for a lot of numbers, no, the mean is varying, and on both the x mean and the y mean are varying. So that's why you get different values from the compared to the Pearson correlation, compared to the Spearman correlation. So that's how you actually you can actually interpret. So whenever because in this case, if you start using, so for relationships like this, if you start using Pearson correlation, you might get values which are not which cannot be easily interpreted, or you might get misleading values. But when you actually want to when you use Spearman correlation, you get values which indicate a trend, okay, whether increasing or the reducing trend and things like that. So that is the main difference between the Pearson and the Spearman. Okay, that's the other thing. Then yeah, ordinal variables, I think explained in the beginning. Ordinal variables are nothing but numbers which like this small. I gave you the example of shirt sizes for small, medium, large, and XL and double XL and all that, where you cannot, so nobody can say that XL is twice. If you ask the shopkeeper how big is XL, he'll say that it will fit. He'll say that for a person like this, it will fit. But he cannot say that XL is 3 times larger than the small, or it is 2 times larger than the small, and things like that. There's no relationship like that. It's an order which is there. Similarly, when you have questions like when they do survey, for example, if they say that the measures taken by the government for COVID is they ask you to rate, then they'll say, somebody might say strongly agree, somebody say agree, neutral, or disagree, and all that. So here again, there is some order to it. You know that strongly agree is bigger than agree, and definitely much bigger than strongly disagree. But you cannot say that strongly agree is 5 times neutral, or strongly agree is 4 times disagree, and things like that. You cannot establish a mathematical relationship. You can only say in terms of an order that this is bigger, this is smaller, that's all. Same is the case with other examples that I gave here. So ordinal is something, there's an order, but there is no mathematical relationship that you can establish. That's the main difference. Now, coming to the example of Spearman correlation coefficient. Here what I've done is I've taken some students. Okay, 17 students are there, and the marks obtained by them in an examination are tabulated. Okay, the marks obtained by them, somebody got 70, somebody got 99, and things like that. Now what you can do is uh, you can there is an Excel function which actually, see, if you want to arrange them in ascending or descending order, you can easily do it. You just have to there's a function you can apply, and then you get them in ascending descending order. But Excel also gives you a way of finding out the order of that number or rank of that number in that particular data set. For example, if in when you actually do your tabulation of marks when you evaluate students for examinations, suppose you total the marks obtained by students in all the subjects, and out of 1,000, for example, if somebody gets 850, somebody gets 700, somebody gets whatever numbers, then how do you decide the ranks? You put them in a descending order. Somebody is scoring the highest, which is 850, he gets the first rank, or somebody getting 825, he might get the second rank. You have a order, and then that's how you rank the students, right? Based on the number that is obtained. Or you take an entrance examination where the MSET examination where they score it for, or a JEE mains examination where they have some score of say 500 or whatever, and whoever scores say 450, which can be the highest, he gets the first rank. That's how they order they give the ranks to the particular students. Now in Excel, using a rank function, you can actually achieve the same thing. So you can apply the rank function rank. You can choose the data for which you are asking Excel to give the ranks. Then and then when you apply the formula, you get the rank of that particular student. Okay, for example, when I ordered this in terms of the rank function, I got in terms of descending order, the person who gets 99 marks, he got the first rank. Similarly, the other next 95 person who got 95, he got the second rank. So similarly, the next guy will get the third rank, and so on. So without you doing all that, Excel, by using a rank function, automatically it will give you the ranks of the students. As simple as that. Similarly, you can do it in ascending order also. For example, if you want to find out from the bottom, somebody is scoring the lowest, he gets a mark of 4. He gets the first, he's first in the order because his marks were the lowest. Similarly, highest 99 would be 17 students in the class. This guy got 99, so he would be 17th placed when you put them in the ascending order. So depending on whether you want it in the ascending order or descending order, you can actually rank the students or whatever numbers that you have by applying this rank function. Okay, applying this rank function. There's another thing called average function, which is, for example, what it does is when suppose two students get the same marks, somebody gets 80, another person also gets 80. What it does is it gives them the same rank, but what it does is it averages the rank, and then it gives a number of 4.5, like that. Between 4 and 5, it gives it 4.5. Like this, it does the averaging. Like this, Excel has several functions to find out the ranks. Okay, the ranks of the numbers that we are dealing with. Now, once you rank them, it's a very simple thing. You just have to apply this formula. This is the Spearman formula. R is equal to, or rho is equal to 1 minus 6 times the d square by n into n square minus 1. I'll explain what each of them in this example I've given. For example, there are say 9 students in a class, and roll number 1 to 9, for example. These guys got first student got 35 marks in maths and 30 in physics. Similarly, he got 23 in maths and 33 in physics. Like this, he got some marks. Now, what we are trying to do is we are ranking this student in terms of the marks obtained. You use this rank function in Excel, and then you can find out the in the descending order. The person who gets the highest marks will get the first rank, and so on. So you rank them in the descending order. Okay. Now, next, the same for physics also. You do the same thing. You rank them in this order, and D is the difference between the ranks obtained for these two students. So what you do is you subtract the rank of the student obtained in maths and the rank of the same student, his rank in physics. When you subtract 3 from 5, for example, you get -2. Similarly, for the second record, you get 2. Like this, you find out the differences. So simple. You find out the ranks from using this Excel function. Okay. For each of these data, the X variable and the Y variable, then find out the difference in the ranks, and then you square the difference in the ranks d square, you get a positive value. So once you get this value of d square, that's it. The formula is done. You just have to apply this 1 minus 6 into d square is the d square value that you just found out. In this case, it is 12. So 6 multiplied by 12 square divided by n is the number of observations, which here it is 9 observations. So it becomes 9 into 9 square minus 1. Once you do that, you get the value of the Pearson's, the Spearman correlation. So that's how you can compute the value of Spearman correlation. Here you can find that the value of Spearman correlation is 0.9833. Okay, so that's how you get the value of Spearman correlation by finding out the rank. So you can think of this in terms of several day-to-day examples that you find, because you suppose a shopkeeper, he wants to find out whether there's a correlation between the sales of shirts and the sales of some other item. Okay, example. Okay, and sales of pants, for example. Now, what he can do is he can at the end of the day, or for a month, he can tabulate how many shirts of M size have been sold, how many shirts of S size have been sold, how many shirts of XL size they've sold. Like this, he can rank them. Okay, he can put them. Then he can rank them in an order. Okay, in that shop, maybe in a particular month, he finds that the sale of L size shirts have been the highest. They get a rank of 1. Similarly, S or the medium shirts, it's been second. They get a rank of 2, like that. Similarly, there's another product also which is trying to see if there's a correlation. Is maybe the pant sizes. Pant sizes again can be whatever different types of pants can be there of different sizes. He ranks them again, and then when he finds out the correlation, then he might get a value of say 0.9. I don't know what value you can get. He might get any value, but if you get say a value of a 0.85 or 0.9, then he can infer that okay, there's a strong correlation between the pants and the shirts sold, which means that people who are coming to shop to buy shirts, they're also buying pants, and vice versa. People who go to the shop to buy shirts, they're also buying people who go to the shop to buy pants, they're also buying shirts. So you get a correlation like that. Whereas you imagine if you can you do the same thing with Pearson? No, because Pearson you cannot compare the sizes. Okay, compare the sizes and give ranks. That's a problem in Pearson. Okay, so that's how you can apply these two in two different contexts, and you can do the same thing in academics also. For example, if you're able to rate students, for example, in a school or a college, if some students will be good in academics, some might be good in sports and other extracurricular activities, and suppose you want to find out there is a correlation between the academics and the extracurricular sports activities. What you can do is, if you're able to rank the students in terms of the academics and in terms of the extracurricular activities, you can find out a Spearman correlation to find out if at all there is a correlation between these two values. Does it mean that people are good in academics, they're also good in extracurricular, or people are good in academics, they're not in extracurricular? People are good in extracurricular, are they not good in academics, and things like that. So you can think of so many examples in your day-to-day life where you can apply this concept of Spearman correlation and come to inferences. So as I said, each of these values, each of these have different applications in real life, and Pearson or the Spearman that we have just learned. So there's another correlation which is called normally I don't know whether we are able to follow, but because we are trying to pack up so much in a short span of time, I have to ensure that I cover these topics, correlation and regression. I might go a little fast, I'm not very sure, but please bear with me. I hope you will be able to understand at least the gist of it, so that you can actually people who are interested can continue by reading books and all that stuff. So the other correlation,
sir, excuse me, sir, sorry for the interruption.
No problem, sir.
If it is possible, can you give 5 minutes break like that? If the participants they're asking.
Yeah, we'll give it for 11:30, sir. Now 11:24.
Yeah. Yes. Okay, sir. Okay, sir. Thank you. Continue. Okay.
Yeah. Just 5 minutes.
Okay.
Right. And the third one that in this topic of correlation is Kendall's correlation. As I said, we learned about 3 types of correlation. One is the Pearson, the other is the Spearman, the other is the Kendall's term. Now, this Kendall's correlation is also like Spearman correlation. It helps you in getting the correlation value for. It's also a rank-based correlation, and I'll show you in what context this is useful. Okay. Now, this Kendall's correlation uses a slightly different concept. In the Spearman, what we have done, if you recollect just now, the Spearman, what we have done is we have given ranks to the observations, and then based on the difference in the ranks, we computed the value of the correlation, 1 minus 6 sigma t square by n into n square minus 1, that formula, you get the value of correlation. That's simple. Now, in Kendall's correlation is slightly different method of calculation of the correlation. It is based on the concept of concordant and discordant pairs of observations. Concordant means the observations that either go up together or go down together. Okay. Discordant means for example, if you take the weight and height of people, if the height goes up, if the weight goes up, then there is a concordant relationship. But if the height goes up and the weight goes down, it doesn't happen normally. But you can think of other variables where the same example of temperature and sales of coke and sweaters. Temperature goes up, sales of coke goes up, which means that both are concordant pair. It's a concordant pair. One goes up, other goes up. A discordant pair is one is going up, other is down. Like coke and sales of sweaters. Temperature and sales of sweaters, one goes up, the other goes down. It's a discordant pair. Okay, that's the difference. Now, given that, I'll just show you how we can calculate Kendall's tau and the context in which it can be used. For example, Kendall's tau, there are say in this example there are say five people A, B, C, D, E. Okay, so what we have done is we have ranked them by height. For example, how do you rank them by height? You find out the heights of these people. Somebody says I'm 5'7", somebody says I'm 5'9", somebody says he's 6 feet, somebody says I'm 4'10". You rank them in terms of some order, ascending or descending order. So in this case, assuming that the person with the highest height is ranked as 1. So suppose A is 6 feet, you put him in the first rank. B is 5'11", you put him in second rank. Somebody is say 5'4", you put him in the third rank. You rank them in an order like this. Similarly, by the weight also you rank them. The same people, when you rank them by height, suppose the person A, though he's the highest, tallest guy in that group of 5 people, by weight he may not be the person with the highest weight. Okay, he might be third in that rank by weight. Okay. Similarly, the person C, his height is third. Maybe he's 5 feet 6 inches tall, and he might be third in that in the rank of rank by height. But he might be 120 kilos, which means that he is the highest by weight. So when you rank these people by height and the weight, you get some numbers like this. Okay. Then what we do is we find the comparison of the height and the weight for every pair. For example, you compare A with B, A with C, A with D, and A with E. Similarly, B with C, B with D, B with A. So you compare all these pairs together in terms of pairs. And then if A and B, the height and weight comparison is going up. For example, if height of A is more than the height of B, and the weight of A is more than the weight of B, which means that both are going up together, like the sales of coke and the temperature, both are going up together. That means that it is concordant. But for the pairs which don't go up together, one goes up, the other goes down, like the temperature and the sales of sweaters, then it's a discordant pair. So what we do is we find out pairs like this. So in this of 5 observations, you get 10 different combinations, and you find out the number of concordant 6 pairs, discordant 4 pairs. Then Kendall's tau is very simple. Number of discordant concordant pairs 6 minus the number of discordant pairs 4. 6 minus 4 by n is the number of observations. There are 5 observations, 1, 2, 3, 4, 5. So 5 into 5 minus 2, you get a value of 0.2. So that is the value of Kendall's tau. So you have to compare like this, and then you can find out the same example you can use for the academics versus the extracurricular activities. For example, you rank somebody good in academics in terms of rank 1, 2, 3, 4, 5. And suppose you are trying to assess their extracurricular activities, painting or drawing or sports and all that, and you rank them by that particular variable, then you get some numbers like this. So when you actually do a comparison like this using Kendall's tau, then you get to know what is the value of correlation. Okay. So the Pearson correlation and Kendall's correlation, they are useful for rank variables like this, where you are ranking the variables in terms of 1, 2, 3, 4, 5, or in ascending or descending order, and getting the values. So that's the main concept behind correlation. I think we have come to the halfway mark. So sir, we can take a break now at 11:30, and you can tell me after how much time we can reconvene and start the class.
Hello.
Yeah, now it's 11:30, sir. We can give a break now.
Yes, sir. Yes, sir.
Yeah.
Okay, sir. Thank you, sir.
Thank you. We can convene at 11:40 or whatever, 10 minutes or.
Okay. All the participants, please take 5 or 10 minutes break. We will start again 11:40. The session will be restart. Okay.
Okay.
Thank you. Thank you, sir.
Thank you.
Please have coffee or tea,
Yeah,
because directly we are not able to give you.
No, I know. I understand. Yeah.
Okay, sir. Thank you.
Thank you, sir.
Take break, sir. Thank you.
Yeah, take a break.
Sir, Srinivas sir.
Yeah, yeah.
Welcome back, sir.
No, thank you.
Uh,
Can we start, sir?
okay, can we start, sir?
Yeah.
Okay, sir. Thank you, sir. Please continue, sir. Thank you.
Okay. Yeah. So we have learned about those three correlation methods and finding out the value of the correlation. I'll just wind up this correlation topic with this last example. Example, this is a what you see. Okay, I'll just share the Excel sheet. I hope you can see the Excel sheet.
Yes, sir. It is visible, sir.
Yeah. So basically, this is a simple data set having of cars where they've given the miles per gallon, the mileage of the cars, and then of different models of cars, the number of cylinders in the car, either 2, 4-cylinder, 8-cylinder car. Displacement is the value of I think it's a stroke length or whatever, and then the horsepower of the car, the weight of the car, acceleration, model, and then the origin must be some country. And different car models are there. So this car data set, I just took this to show you how we can actually calculate the correlations between variables. For example, if you do the find out the correlation between weight and miles per gallon, now you can apply this Pearson's correlation from the Excel formula. I just have to choose the weight and the miles per gallon. I just have to choose, I just put the formula is equal to Corel and select the two columns. One is the miles per gallon, the other is the weight. And you press enter, you get a value of minus 0.8317. Now, two things. First thing is, as you can see, the value is between -1 to +1. So it is within the limit. That's one thing. And it is 0.83, which means that there's a strong correlation between the weights and the miles per gallon. And the other important thing you would have noticed is the negative value, indicating that the more the weight of the car, then the lesser is the mileage given by the car. Okay, so more the weight, lesser is the mileage. So that negative value indicates that there's a negative correlation between the two variables, that is the weight and the miles per gallon. That is also commonsensically also it makes sense, because as we know, if the weight of a car is more, the mileage will reduce. Okay, that's one thing which is also visible, or one thing which you also can see from this particular correlation value. And similarly, if you look at the correlation between cylinders and displacement, you get a positive value. And the cylinders and miles per gallon, okay, more the cylinders, that is, suppose you have normally in our cars, it's if you take a small Maruti car, Alto car, it is a 3-cylinder engine. If you take a bigger car, it can be a 4-cylinder engine. If it's a big BMW, there'll be 6 cylinders, 8 cylinders, depends on the type of car. Now, if the number of cylinders are more, then the miles per gallon is also reducing, because they consume more petrol or diesel. Okay, so that's why you get a value of 0.775, which is high, but you got a negative value indicating that there is a negative correlation between the miles per gallon and the number of cylinders in the car. Like this, it's very simple to calculate the correlations using the Excel of Pearson's formula. Just take the formula, then choose the particular columns or rows, and then you get the value of correlation. So as simple as that. What is more important is understanding and interpreting these values. First of all, finding out, yes, the value ranges between -1 to +1. Number one. Number two, how strong is the relationship based on the correlation value. Suppose the correlation value is 0.2 or 0.1 or 0 or -4, something like -0.25, like that, then you say they're not highly correlated. But if the value is closer to -1 or +1, that is on the extremes, then you say they are strongly correlated, number one. Number two, the plus or minus sign indicates whether they are positively correlated or the negatively correlated. That's the important things that you have to interpret from the correlation values. Right. Now, having finished this, I'll just move on to the next topic, which is regression. Okay. Regression. Now, regression is another important topic that we learn in statistics, especially regression is one of the first machine learning models that is being taught, that will be taught to students who are learning data science, okay, as a part of the statistics course. Now, regression, as I said, is the most commonly used model, number one. And why it is used is it's a tool for finding out the association between two variables, X and Y. Now, in correlation, remember, we are finding out the strength of the relationship and whether the relationship exists and the strength of the relationship. Now, here in regression, what we are trying to do is we are trying to go to the next step, which is finding out what is the equation that describes this relationship. Okay, correlation, you are only getting the strength. Based on the correlation value, you can say yes, it is strongly related, it is positively correlated, it is negative correlated, and interpretations like that. But then the next question would be, can you express this in terms of a mathematical equation, which you can apply and find out for values that come up in future? So that's the use of a regression analysis. Okay. Now, in regression, in correlation, you remember we were all dealing with linear relationships, but in regression, the relationship you're trying to find out between two variables or multiple variables also is you apply it both for linear as well as non-linear. So it means that this red line that you see in the presentation, it can be a red straight line, it can be a curved line, or whatever relationship. It can be linear as well as non-linear. And again, regression also, like correlation, it only shows the relationship between the two variables, but it does not indicate a causation. It doesn't mean that the traffic in the city and the sales of air conditioners, if you plot them like this, you get a line, you get some line, but it doesn't mean that this is causing that. So it does not imply causation. Okay, that's the other point that you have to remember. And coming to the terminology, normally regression, when you talk of a simple linear regression, we talk of two variables, okay, X and Y. If you talk of multiple linear regression, then you talk of one dependent variable, which is Y, and then you have so many independent variables, X1, X2, X3, and so on. For example, the same example of sales of Coke, it can depend on temperature is one thing. It can also depend on the population in that particular area. It can depend on the income levels in that particular area. It can depend on so many factors, right? So simplicity, we have taken one, but one dependent variable can be influenced by several independent variables. So you can have multiple ones. And nomenclature that is normally used is dependent variable, independent variable. So dependent variable is the Y value, which you plot on the Y axis, and independent variables are plotted on the X axis. So they are called by several names. All of them they all mean the same. You can call them in some books they might write dependent, some books they might write explained and explanatory, some they write predicted and predictor. Like this, you have several nomenclatures which are used to define these independent and independent variable. They mean the same. Okay, so there's no confusion when you encounter any of these different nomenclatures in different textbooks or whatever literature that you read. Now, coming to the types of regression, they can be divided into two types, major types. One is a simple linear regression, and the other multiple regression. A simple regression is you have one independent variable, and when you're trying to establish the relationship between height and weight, for example, if your height is the x-axis, which is the independent variable, the weight can be the y-axis, which is the dependent variable. So whenever you encounter one independent variable, then it's a case of simple regression. But if you have more than one independent variable, then it's a case of multiple regression. So if you're trying to find the relationship between the sales of Coke and the temperature only, then it is a simple regression. But if you're trying to plot what can be the regression between sales of Coke when you have independent variables like temperature, population, income levels in that area, age group of people in that area, because sales of Coke or any item for that matter depends on so many factors, not just on temperature. For example, you have a lot of youngsters who are in that locality, then the sales of Coke might be influenced by that. So you have different models which different independent variables that influence the dependent variable. In that case, you go in for multiple regression. And in simple regression and multiple regression, again, you have two types. One is a linear and the other is a non-linear. So again, multiple, you have linear and non-linear. Linear is when you have a linear relationship. Non-linear when you have a non-linear relationship. So all these models are learned as part of the analysis. Okay, but for today's class, since we have a limit of time, I will run you through a simple linear regression model. So once you understand this, the other models are almost similar. There's no rocket science. You can easily interpret and understand. So that's the reason, given the limitation of time, I've decided to go with the first topic, which is simple linear regression. Okay, that is where we deal with one independent variable, and the other, of course, is the dependent variable. So you have an x value, which is the independent variable, and y value, which is the dependent variable. So this is what we will learn today. Now, simple linear regression, as I just said, you have an independent variable, you have a dependent variable. So y is equal to, people who are familiar with mathematics and people who have studied MPC in their +2, you are familiar with the equation y is equal to mx plus c. That's a very one of the first equations we learn in straight lines. Okay, y is equal to mx plus c, where y is on the y-axis. In this case, it is the dependent variable, and x is obviously on the x-axis, the dependent variable, and m is the line, and c is the intercept on the y-axis. This is the common, or one of the first equations that we learn in our +2 mathematics course, right? Now, simple linear regression uses the same equation. Now, what it does is, when we're trying to establish the relationship between one independent variable and one dependent variable with a straight line, and how we plot the straight line is, first what we do is we draw up a scatter plot between the independent variables and the dependent variables. For example, when I say a scatter plot, for example, if you are trying to plot the heights and weights of people, first person's height is 5 feet 5 inches, his weight can be 65 kilos. Next person can be 5 feet 9 inches, his weight can be 72 kilos. So you take each of them as an x value and a y value and plot them on the graph. Okay. Now, once you get that graph, that's called a scatter plot, because the points are all scattered around. So that's why it's called a scatter plot. Now, in that, using that scatter plot, you try to fit a line. You try to fit a line, and that line, I can suppose you can draw a line in one way, I can draw a line different way, and we will see in the next few slides how we actually draw the line. It's not that I can draw a line in one case, somebody in a different way. You can have infinite number of ways in which you can draw the line through the points, but there is one line which satisfies certain criteria, which is called best fit line. So we will see how that line is actually drawn to establish the relationship between the x variable and the x value and the y value, which is the dependent variable and the independent variable. Now, the next question is, where where can you use linear regression? It can be used in a number of applications. For example, if the sales of a product, it can be one case, or predicting trends and forecasts can be one thing, or if somebody is trying to find a marketing campaign, somebody spends money on TV advertising, he wants to find out whether the sales of his products have increased or not, or maybe house prices with the price of houses. There can be n number of applications of linear regression in a day-to-day life. You can also find them in, you can also probably, when you in subjects you teach, you can think of so many examples where you can use linear regression to find relationship between the dependent or independent variables, and then whenever you encounter a new value in future, you can actually predict how much can be the dependent variable, because you established the relationship. Right. Now, how do we draw this line is the next point that we wanted to understand. What this regression does is, it when you have a number of points, as I said, when you plot you take the same case of x values and y values, when you plot them, you get a scatter plot, and then you have to draw the line through these points in a certain way. Now, how that is drawn, the best fit line is drawn based on certain principles. What the best fit line does is, when you draw the line, you should see that it minimizes the distance of the line from each of these points that you have. For example, if I have to draw a line, yeah, if I have to draw a line, like, for example, somebody can say that I'll draw a line like this. Somebody will say I'll draw a line like this. Somebody will say, no, I'll draw a line like this. Okay. Somebody will say I'll draw a line like this. You have n number of lines you can draw through the same set of points, right? through the same set of points. Now, but what is that line? This line, which is called the line of best fit. This line of best fit is the line that minimizes the distance between the given points and this particular line. Okay, so there can be one line which minimizes the distance. So that's called the line of best fit. How it does is, now somebody, suppose I draw a line like this. Okay, or I'll just show it once again. I draw a line like this, and annotate, and yeah, suppose I draw a line like this. Okay, a line like this. Okay, now when we have the points, the different points that we plotted, and I've drawn this line. Now this line, the distance from this line to each of these points, when you find out, there is some value. For example, this point will have a coordinate of something 2 and 7, but my line, when I draw the line which I've drawn, it is at, say, 5 point something. So the difference between 5 point something and 7 is something called the residue. And similarly, between the line that I drew and each of these points, you get those values. When you square them up, you get some number. Okay. Similarly, somebody will say that no, that your line is wrong. Let me draw a line like this. He'll say, let me draw a line like this. So even for him, he finds out the distances between the points and this line and squares them up. He gets a number. And so like this, each of us can draw lines, and then each of us can get that value of the residue, the so-called residual sum of squares. Residual sum of squares is nothing but that leftover value between the line and the y-coordinate of the line and the point. The value that you have left over is the residue, and when you square them up, you get something called the residual sum of squares. So that residual sum of squares should be as low as possible. So I might get 15, somebody might get 3, somebody might get 24, somebody might get 0, or somebody gets 2.5, somebody gets minus. So he cannot get minus because we are squaring up the residuals. That's why it's called the residual sum of squares. So the reason why you are summing up, you're squaring that, is because you get a positive number. Otherwise, what happens is, if you just add up the residues, the top values will be, for example, if the line is below a certain point, then the residue can be plus. If the point is below the line, the residue can be minus. So when you add them up, you might end up in getting a 0. So instead of that, what you do is, for every residue, you square up the residues and sum them up so that you get a positive value. So that positive value, the line for which that positive value of the residual sum of squares is the minimal, is the line of best fit. So that is how we draw the line. Now this particular line that has been drawn is the line of best fit, because the residual sum of squares between the points and the line are the minimal. So that's how this line is drawn. So we don't have to draw it. The statistically, the Excel tool or whatever, they can do it. But the concept is that. Now what happens if you look at this equation? The y value, which given by the line, the predicted value, is equal to intercept. The same equation we learned in our +2, y is equal to mx plus c, where c is the intercept on the y-axis, and beta, or there it is m value, which is the slope. So slope into the value of x plus the beta naught, which is the slope, which is the intercept on the y-axis. You add them up, you get the value of the predicted value on the line. Okay, now that's how. That's how the entire thing. So this method is called the ordinary least squares method. It's called least squares because you're trying to find out the squares of the residuals and sum them up, and the one that gives you the line that gives you the minimal, the least squares, the RSS square value, the RSS residual sum of squares value, is the line of. That's how this line is drawn. Okay. Now you have different terminology, which is RSS means residual sum of squares, and as I said, residue you can find out by subtracting the value of the point. Suppose in this case, the second point, for example, the x-axis x coordinate is 2 and y coordinate is 7. So and the point indicated on the y-axis for this line is 4. So when you subtract 7 from 4, you get 3. So 3 square is the residual square. Similarly, for the other point, you might get a residue of 2. 2 square. Points below, you might get a residue of -4. -4 is the sum of the square. So you add up all these squares, you get the residual sum of square. That's how this tool finds out the best fit line. Okay, now Now, so I'll explain how where we use this in practice. I'll show an example also as to how you can find out these values. Now, as I said, in correlation, what did we learn? Apart from learning the formula, first we learned the concept of correlation. Then we learned that we learned a formula, which is Pearson correlation or Kendall's correlation or the Spearman correlation. And then after that, what we learned is based on the value that you get, you are able to establish the strength of the correlation, which is -1 to +1 based on the value. If the correlation is 0, you know that it's a perfect straight line. There's no relationship at all. Similarly, for linear regression also, there are some metrics that you actually take up to find out the strength of the relationship. So two important ones are, one is the R-square value or the coefficient of determination. The other is the residual standard error. So based on these values, you can actually determine the strength of the relationship. Okay. Now, what is R square and all? I'll explain the help of a Excel exercise where you will be able to appreciate how this is actually calculated. Okay. Not exercise. It is yeah. Yeah. So if you can see from this graph, from this Excel sheet, now this is a data of, if you follow this carefully, this is a data of the height and the weights of people. Okay, heights and weights of people. Now heights are on the x-axis, it's an independent variable, and y is the dependent variable, which is on the y-axis. Okay. Now, when you are, I've taken some records. I think 15 people's heights and weights I've plotted. 15 people whose first person's height is 183 centimeters and his weight is 77 kilos. Similarly, height is 168 for the second person and the weight is 71 kilos. So you have 15 people in all. Okay. 15 people on total in this particular data. You can have any number as possible. There's no limitation. Now, out of 15 people, the heights and weights I've plotted. Okay. Now, in Excel, you don't have to, when you want to plot the regression line, first of all, what we can do is we can plot the graph. You can plot the graph. In Excel, it's very simple. People who are familiar with Excel, it's not a problem. But for people who are new to Excel, I'll just show you how it is done. This data, select this data of the height versus the weight, this data. And what you have to do is you just have to, there's a way of drawing the plot. It's called a scatter plot. Okay, so it's called the scatter plot. You just choose the scatter plot, and then you can do all the cosmetic things like naming it and all that. So you just have to draw that, and then now you got a scatter plot, right? So here the height is plotted on the x-axis and weights on the y-axis. You can also change the scales and all that. All these. Suppose you want to graph to come closer and all that manipulation you can do. But given the shortage of time, I leave that to you. But suppose using the same graph, using the same data, I want to plot the regression line, for example. I just have to select one of these points. They get highlighted. I right click and I say add the trend line. Okay, add the trend line. So once I add the trend line, then I also have other options which I get on the right hand side. It also says, it also tells me other, it also gives me other options like display equation on the chart and display R square value in the chart. Okay. Once I do that, then I'll be able to get the values on the graph itself. So here you can see that the Excel has fitted the regression line. People are familiar with +2 mathematics. They'll find this to be very simple. Actually, it's not. All you see, Excel has come out with this equation of the regression line. So what does the regression line did? As I said, it is trying to find out the line that minimizes the residual sum of squares. So from each point, if you take the distance from the line, y-axis, the y coordinate of the line to the y coordinate of the point, so there is some value. You square up the value of the, so this distance between the point and the line is called the residue. So square up the residues and total up for all the points, you get the residual sum of squares. So based on Excel or any other regression tool, what it does is it does this method and then finds out the equation of the line. So in this case, you can see that it's in the form y is equal to mx plus c, the familiar y is equal to mx plus c equation that we have learned in our +2 days or whatever, y is equal to mx plus c, where you know that m is the value of the slope. It is 0.9861 and C value is the intercept, which is minus 106.27. And R square value is the quotient of determination, which we will learn as to what is its significance, 0.4753. What does it mean? So this we will learn in the theory part. Now, so as I said, I showed you how this regression line is plotted. Now I did the same thing here. I got the regression equation, y is equal to 0.9861 x minus 106.27, and R square value is 0.4753. The same data, I have modified the scale. In Excel, you can do all that manipulations, because remember in this graph, the scale was starting at 0. So your graph was somewhere on the right hand side. So, but in this case, I have started the scale from 140 itself, so that my graph came to the left hand side. You can do all those manipulations in Excel, and you can ensure that the graph looks better in terms of the interpretation. So this line which I've drawn, Excel, I didn't draw this line. Excel has itself fitted the line of best fit. And it has also given me the equation of the line, which I've shown you how that equation is arrived at. It has fixed the line in the form y is equal to mx plus c, and R square value is given. It's all computed by Excel, right? Now, now you find that in this there are three important values that have to be remembered. First is the mean. What is mean? All of us are familiar with mean. Mean is nothing but the average. Okay. Now there are 15 people in that data, and they have certain weights. So when you find out the average weight of these 15 people, you get some number. So you plot that line on the graph, on this graph, you get a line correspond, and you call that the mean. Okay. Why this mean is chosen is, this is sort of a base. Why we choose mean as a basis? Because normally, suppose I was giving the example of the marks obtained by students in a class. Suppose somebody gets out of 100 marks, somebody gets say 57 in economics, somebody gets 87 in economics, and things like that. So if you tell me those 100 numbers, I get lost. Okay, but if I ask you what is the average mark obtained by students in economics, then you would say, okay, this people got 68.5. That is the average mark. And if I want to compare that with some how much they got in say commerce or some other subject, then you would say, suppose you say it is 75. Then I realize that okay, people are able to score more in commerce than in economics. So based on the mean value, I'll be able to give you some conclusion, because that gives me a average value from which I can draw some conclusions, right? So mean value is taken as the base. Here also, in this case, the y value, which is the weight value, we are, because on the y-axis, we are taking that as a base, and then we are drawing the mean. That's a base value. Now, and from the mean, when you subtract each point, see, your line has passed through the points in a certain way, but you can observe that the line has not passed through all the points. Some points are below, some points are above. Maybe it is a coincidence. It can be a coincidence that line might pass through 1 or 2 points, but most of the points, some will be above, some will be below, and like that. As I said, how does the line go? Why not the line go? Why doesn't the line go above all the points? Because if it goes above all the points, then the residual sum of squares will be very high. Okay, and similarly, the line can go below all the points. Again, the residual sum of squares will be very high. So a line drawn in any other will definitely not be the line of best fit, because the residual sum of squares will be high. So this line which Excel has drawn is the line of best fit, because the residual sum of squares is the minimum. Now, what is the residual sum of squares? It is a difference between the value given on the line, minus the actual value of the y value. For example, if this particular point corresponds to a weight of say 82, but the weight predicted by the line or weight indicated by the line can be 74. So the actual weight of the person is 82, but the weight on the line is only 74. So there is a residue of 8 kilos left over. Okay, that's a residue. Similarly, if you take another point, the weight predicted by the line or weight estimated by the line can be 70 kilos, but again for the same person, the weight is only 50. The actual weight is 50. So there is a residue of nearly 20 kilos. So this 20 square plus the 8 square, like this, you find out the residual sum of squares for all the values. You get the total, that you get the residual sum of squares. Okay, that is one value. Okay. Now there's another term called total sum of squares. What is total sum of squares? It is nothing but the difference between the value which is given to us, that is the y value, and the mean value. So when you find out the difference and square it up and add up for all the values, you get a value called the total sum of squares. It's called TSS. Okay, so now you have two terms, three terms, in fact, mean, which all of us are familiar with. Then you have a total sum of squares, which is nothing but the difference between the actual value of y and the mean value. For example, here in this case, you have actual value of y as 77, 71, 50 and all that. You also have a mean. Okay, mean is, if you want me to compute the mean, just have to press the average value, and you just have to choose these numbers. Then automatically Excel will find out the average value. 63.9 value, which I found out here also, not needed. It is there as mean 63.9. So the difference between each of the y values and the mean, okay, you square them up, you get the total sum. Okay, you have so many numbers, you have 10 observations or 15 observations. For each of them, you find out, square it up, and add for all these 15, you get the total sum of squares. Now, residual sum of squares, I already told you, from the given value, you subtract the value predicted by the line and square them up for all the values, add them up, you get the residual sum of squares. Now, this is enough for you to calculate the R square value, which I will just explain. Now, if you look at this graph, as you know, this graph, the Excel is able to predict the linear regression line, which is y in the form of y is equal to mx plus c, where m is the value of the slope, which is 0.9881, and the value of beta naught is the intercept, the c value, which is minus 106.3. So if you suppose you ask me what will be the height of or the weight of a person, suppose in this data I've been given data for 180 centimeters, weight is 77, is 163 centimeters, his weight is 60. Suppose you say, what if a person has a height of say 160 centimeters? That 160 centimeters data is not there. So how do you estimate the weight of the person from this height of 160 centimeters? You put that number in the regression equation, and then you can estimate what will be his weight. For example, if y is equal to, suppose I give you a value of, you ask me what will be the weight of a person if his height is say 160 centimeters. So 160 centimeters. So what I do is I have to multiply y is equal to mx plus c. The slope is 0.9861 into the value of the height is x value. The first is the slope value, m value, multiplied by is equal to m value, which is the slope of the line, multiplied by x value, which is the height of the person, plus the c value, which is the intercept, which is this much. So you can say that for a height of 160 centimeters, the regression line is predicting a weight of 51.560 kilos. The weight is 51.560. So by using regression, you will be able to estimate the dependent variable for values that are not given in the data. For example, if somebody says that, tell me what will be the weight of a person who is 180 centimeters or 185.6 centimeters tall, then you can get the value from the regression line, which is 76.7. I did not do anything. I just applied the equation, which is given by this line, and then I got a value of 76.75016 or whatever. So suppose somebody is say 7 feet tall, which is 210 centimeters, then his weight will be 100.811 kilos. So you can estimate based on any new value that you get, you can estimate the value of the weight. So this you can apply to anything. The same example of Coke, of the sales of Coke and temperature. If somebody you can fit a regression line for the sales of Coke and the temperature. And when you get the regression line, somebody says that, okay, tell me what will be the same Coke if the temperature is say 42.5 degrees centigrade. Then you put that in the regression line, you will be able to get the approximate value of the sales of the number of cases of Coke that can be sold. So normally these companies usually use different parameters, but temperature is definitely one of the parameters. Suppose you are selling packaged mineral water bottles like Bisleri or whatever, any company. So definitely temperature influences the sales of these bottles a lot. So they would be very carefully watching what will be the temperature on every day. So they know that if the temperature goes up to 45 degrees centigrade, it will go up that much. So they obviously would plan for their supplies. They would plan for the production and supply and all that stuff. So it actually helps you in estimating values like this. Okay. Now you can find out these values like this from the regression line. And now I'll show you how these calculations are done. For example, this estimated value which regression line is predicted is based on the equation y is equal to beta naught plus beta 1x. As I just mentioned, Beta naught is the value of the intercept on the x-axis, on the y-axis, and beta 1 is the slope of the line. So when you apply this formula, just I showed you now, when you apply for a height of 210 centimeters, I got a weight of 100 point whatever, and applying the line. Similarly, what I've done is I've applied the same equation for all these points, and I got the predicted value based on the regression. I got these numbers. Now, what did we learn is residue? The residue is nothing but the actual weight, actual value of the dependent variable y minus what has been predicted by the line. Okay, so this difference of RSS which you see on the graph, residual sum of squares, the actual value is indicated by the points. That is the data given to you. That is a base. That is the data which you plotted in the form of a scatter plot. That is the value given to you minus the value predicted by your line. So the difference is the residual error. That's the residual error. Now we know that somebody raised a hand. Any questions, sir, from Mr. Ravi? Yeah. Okay. Now, so we know that so residual sum of error square is what you I just squared up these values in the column F. So 7.92 is the square of the residual error, and for each value you can find out what is the square like this, and then residual sum of squares. As I said, it is a residual sum of squares. So what we do is we somebody is raising a hand, sir. Muniswamy, sir. Should I stop or any doubt? Or is it just
yes, sir, I have doubt.
Yeah, please. Yeah.
Sir,
Yeah,
when
sir.
do we use this formula, sir?
Which one, ma'am?
X minus x bar whole square is equal to b of xy, y minus y bar.
Where is that formula?
We use in regression, no, sir. X minus x bar
Yeah,
whole
yeah.
square
Yeah,
is equal to b of xy, y minus y bar.
You can use that, but when you use these tools, you don't have to apply those. See, all those when we were not having all these tools, we were using all that to calculate manually. Now, the same thing you can accomplish using these tools in Excel or any other statistical packages. You don't have to do all that, right? Yeah.
Actually, someone asked me the formula for regression, so I told this formula. X
Formula is
minus
there,
x
ma'am.
bar whole square.
Yeah, correct. See, I in the case of correlation also, I showed you how correlation is calculated. Okay, we have that formula x minus x bar into y minus y bar divided by all that sigma x, sigma y.
Yes, sir. Yes.
Yeah, but what does Excel do? They see all those were there when we were learning for ages, for several hundreds of for decades. Those formulas have been there. Even those formulas are still valid today. Those bases will remain the same. But these tools have come and they've expressed everything in terms of formula, which you can just apply. For example, the same formula of correlation, instead of doing all that calculation, you just have to put correlate and then put the variables, you get the answer. Like this, Excel or any other tool, statistical tool like SPSS, any tool, you just have to choose the data and it will give you the regression equation. You don't have to go through all that process. That equation is correct. What you said is right. I'm not denying that. But,
yes, sir.
But we don't have to do all that manual laborious calculations. Yeah.
Okay, sir. Okay.
Yeah.
Thank you, sir.
Yeah. So I'm doing these calculations for you to understand the concept. Otherwise, we don't have to. I just showed you in the earlier this thing. No, you just have to choose the data and choose the graph, and then it's done for you. It's as simple as that. It's a 1-minute job. That's all. So this is only for you to understand the concept behind each of these terms called residual sum of squares and the total sum of squares and R square value and all that stuff. Now, residual sum of squares, as you know, it is a difference, the residual value square of that, and the total sum of squares is nothing but the difference between the actual value given to you and the mean value. So when you find out the value difference for each of these y values and square them up and total them up, you get the total sum of squares. And then you find out the total. Here it is 1857 and the other is 3538 or whatever. You get the total sum of squares, and then you get the same values, residual sum of squares. Now you understood what is residual sum of squares and total sum of squares. Residual sum of squares is 1857 and the total sum of squares is 3538. So an R square value, which is the one that we are trying to understand now, is nothing but 1 minus the residual sum of squares. In this case, it is 1857 divided by the total sum of squares is 3538. So when you subtract 1 minus 1857 by 3538, you get a value of 0.4753, which is given in the Excel. So Excel has done all that for you. You don't have to I just explained all this for you to understand how the RSS, what do the RSS and the TSS mean, and how are they calculated, and how do you arrive at the value of R square. Otherwise, if I just choose the data and then choose the Excel, it will give me the formulas, but it will not understand that I arrived at. So that is the purpose I've done all these calculations. Now, the next question is, if you look at the value of R square, if you look at it closely, now R square value will be 1 minus RSS, the residual sum of squares, by the total sum of squares. Now, when will R square be high? When, see, from a value of 1, you are trying to subtract some value, right? So when you are trying to suppose from 1 you subtract 1, it becomes 0. Okay. From 1 you are subtracting 0.5. Then suppose from 1 you are subtracting 0.5, you get a value of 0.5. From 1 you are subtracting 0. Suppose from 1 you are subtracting say 1 minus say 0.2, you get a value of 0.8. Or from 1 you subtract a value of 1 minus say 0.9 or 0.1, you get a value of 0.9. So what this tells you is that if you are subtracting a smaller value, you get a higher value of R square. Okay, higher value of R square. So when will this RSS by TSS be small? When the numerator is high, when the numerator is small. So if you want the RSS by TSS value to be small, your numerator should be as small as possible. That means that your residue should be as small as possible. So when will the residue be as small as possible? When your line passes as close to the points as possible. Okay, as close to the points as possible. If the line is able to pass through all the points, then if the line passes through all the points, your residue will be 0, because the point and the line coincide. The difference between the point and the line, if they coincide, the value is 0. But if your line passes in such a way that the points are farther apart, then what happens is your residue is more. So RSS value goes up. So RSS value goes up. What happens? The numerator in this case is more, which means that when you're subtracting a higher value, for example, when you subtract 1 minus 0.9, for example, then your R square value is only 0.1. You're subtracting more bigger value from 1. So what your intention should be is to minimize the residue, which means that your RSS value should be as low as possible. Okay, that's when you get a higher value of R square. So higher value of R square gives you what? It indicates, suppose R square value is 0.9, it indicates, then you understand that, okay, from 1 you are subtracting a very small value. So RSS value, which is the numerator, is small. So this now will tell you that the more the value of R square, better is the regression, the strength of the regression equation that is obtained. Okay, so that is the value of that is the meaning of R square that you learned as a part of this. Okay. Now, yeah, given that. So R square value is that. So what does it say now? R square is a measure of how well the regression line fits the data. I just showed you how you calculate R square from this equation 1 minus RSS by TSS. Then the other thing is R square also tells you what portion of the data variation is explained by the model. You know that, as I said, if the line passes through all the points, which is rare, if it passes through all the points, then what? The line fully explains that, right? The value in any value in the equation, you get the value of y. But if the line does not pass through all the points, which is the normal case, then the line is not able to fully explain the data, which is expected, because no data will be perfect. Okay. Now R square value is between 0 and 1, and then it is the percentage of variation explained by the regression model. R square value, suppose it is 0.9, which means that line is able to explain 90% of the data. The R square value is 0. Here in this example I've chosen, we got R square value of 0.47, which means that it is able to, the regression line is able to explain only 47% of the data, or the variation in the data. Okay. So overall, the higher the value of R square, the better is the fit of the model. That is the fit of the regression line to the data. That is the implication of that. Okay. Let's call it the coefficient of, so you can see from the same Excel, I've shown you in the same Excel. Now on the x-axis, you have the independent variables. On the y-axis, you have the dependent variable. And when you fit the regression line, so you get the classic or famous equation y is equal to mx plus c, where c is the slope and y is, and m is the slope and c is the intercept. So here it is beta naught and beta 1. And the total sum of squares is nothing but the difference between the actual value of y and the mean value, which is the total sum of squares, and the difference between the actual value of y and the line, and the value predicted by the line is the residual value. So that is the residual value, and the squares of all such values gives you the residual sum of squares. So then when you apply this formula, 1 minus the residual sum of squares divided by the total sum of squares, you get a value of r square. And as I just explained, you want to lower this RSS as much as lower as possible, so that the numerator is as small as possible. When the numerator is small, this value of RSS by TSS is small. So when you are subtracting a small number from 1, you get a higher value compared to when you are subtracting a larger number. So if RSS is 0, you get a value of r square as 1. If RSS is RSS by TSS is 0.1, then you get a value of r square as 1 minus 0.1, which is 0.9. So more the higher value of r square you can obtain when you minimize the RSS value. So that's the meaning of this particular thing, and that's how the regression line is actually fitted to the data that you have. Okay. So RSS and TSS are just explained. Yeah. Yeah. Now look at this r square interpretation of r square. If you look at this particular 4 graphs that I've taken, now r square value in the first in the top left corner, when you this regression line, when it is drawn, it is passing through all the points, which means that why did you get a value of r square as 1? Because in that formula, if you remember, 1 minus RSS by TSS, there is no residue at all. The line is passing through all the points. So the difference between the point value indicated by y value of the point and the y value indicated by the line is 0. Difference is 0 because the line passes through the points. So that's why you get a value of r square as 1. Okay. Now you take the second case where the line is passing through. It has been fit. It is only passing through one point. Other points are up and down. So when you find out the value of r square by the same, of course, you don't have to find out the regression tool finds it for you, but manually also, as somebody was suggesting, if you apply those formulas, you can arrive at the same values. But Excel or any of the statistical tools will help you get the same values within no time. So r square value in this case it is 0.7. So you can understand there is a fitment of 70%. So the regression line is able to explain 70% of the variation in the data, or 70% of the data. Similarly, if you go to the third one, which is on the bottom left corner, now here you get a value of r square is 0.36. So you can see that the residues are very high, right? The residues, the line is passing through the points, but the residues are high. So that's why RSS value is high. And when it is high, you're subtracting a higher value from 1, you get a lower value of r square, which is 0.36 in this case. So what happens if you try to move the line up? No, see, the regression line is fit in such a way that the RSS, the residual sum of squares is as minimal as possible. Suppose somebody says that no, I'll push the line a little up above. What happens is he might take the line to the point some which might be close, but at the same time, for example, if somebody tries to draw a line like this, yeah. Suppose somebody says that no, let me push the line a little above. He'll say that no, let me push the line like this. Okay, he'll say that. Okay, if he tries to draw a line like this, then what happens? It might become closer to some points. But at the same time, it will become farther from the other points, which means that your residue from the other points will increase, and RSS will increase. At the same time, somebody will say, let me draw a line like this. In which case, it might be closer to some points below, but it will become farther to the other points above, and then ultimately your RSS will increase. So the Excel or any other tool, statistical tool for that matter, it will try to draw the line in such a way that it minimizes the residual value. That is the value between the actual points y coordinate, and the coordinate of the value predicted by the line. So that's how this regression tools work. Okay. Yeah. So similarly, on the right hand side, you can see that r square value is 0.05. See how there is a line that has been fit by the regression equation, and you see the points are all scattered around, and r square value is very, very low, 0.05, because the residues are very, very high. So when you are subtracting high value of RSS value is very high, when you are subtracting a y value of RSS from 1, RSS by TSS is high. So 1 minus that higher value is giving you a very, very low value of r square, which is 0.05. So I think these 4 graphs will now give you a fair idea of what r square how r square can be interpreted, because r square value will be high, which is the highest of 1 when it passes through all the points on the line, which is very rare. But r square value will keep on reducing as the points become farther and farther apart from the line. which means residues are increasing. The residues are increasing, R square value will keep reducing. Okay, residues are increasing, R square values will keep reducing. You can see that from the second graph, it becomes 0.7. When the points become farther apart, the R square value becomes 0.36, and the points became much further apart, then the R square value becomes 0.05. So that's how the R square value can be interpreted. Okay, that's how now. And there's the same thing in terms of it's also expressed like this: the total sum of squares, which I just mentioned, difference between the actual value of y and the mean value, the total sum of squares is equal to there are RSS you have just learned is the residual sum of squares, and the explained sum of squares is nothing but the difference between the value predicted by the line and then the mean value, which is called ESS. Square it up, you get the ESS. So this equation, so you can see that the total variation is from actual value of y to the mean, which is equal to the residue plus the explained sum of the explained value of the difference. So these two, so these are the main important points in any regression equation. What you have to remember is that how the regression line is fit. First of all, where is it used? And then secondly, how is the regression line fit? And then the third one is how do you measure the goodness of fit, whether it's a good fit for the data given, or is it not is it a bad fit? That you decide based on the value of R square, which is also called the coefficient of determination. That's how the regression is interpreted. Okay. Now, extending this concept, we'll just finish another 5-10 minutes. Extending this concept a little further, as I said in the beginning slides, regression has different flavors. One is starting with the simple linear regression, which you have just learned. To you can have multiple linear regression, and you can have polynomial regression. There are several types of regressions used. The word regression is common, but the types of data is different. So you have different techniques for finding out the regression equations. So what you have just learned is the simple linear regression, but you can also have cases where you have multiple linear regressions. For example, in the case of simple linear regression that we just learned, we have seen that there is one independent variable, which is the x value, which is, in this case, we have seen the value of x as the height person, and the y value is the dependent variable. In this case, we have seen the weight of the person. Okay, so we have tried to plot the relationship between x and y, and we got a regression equation. And you also found that based on the value of R square, you can determine the strength of the relationship between the value of not the strength, the how much this line can actually explain the data. Okay, so R square value was an indicator for that. Okay, based on the residues. Now, what if a case where you have multiple independent variables, like x values? For example, the same example of the sales of Coke, temperature is one variable, the incomes of people in that area is one variable, then population density in that area can be one variable. So there can be many variables which can influence the sales of Coke, which is the value of y in this case. So in that case, when you have multiple independent variables influencing one variable, that is a case of a multiple linear regression. It's a linear relationship, but it is called multiple because you have multiple independent variables. Okay, so you can see from this graph in this, not the figure on the right hand side, what if suppose you have just one independent variable and one independent variable, you can just plot them in our standard coordinate geometry scatter plot, x and y axis. But you have multiple independent variables. For example, you have two independent variables, x and y, or x1, x2, and a dependent variable y. Then you have x, or x, y, z can be one thing, x1, x2, and y can be one thing. So you have one axis, you have two axes at the bottom and one going up, like a room. No, you have a parallelepiped or something where you have two axes. You have plot one thing on one axis, second independent variable, and the dependent variable vertical or whatever. You have two independent variables in this case, but you can have multiple independent variables. You can have 10 or 50, even 100 or 200 like that. But for human eye, we can only visualize up to three dimensions. We cannot visualize more than 3 dimensions. So you cannot actually plot for more than 3 dimensions on a paper or your own computer. We cannot visualize them. So you just have to imagine that there can be more than 3 variables. In this case, there are 2 independent variables and 1 dependent variable. You can have multiple independent variables actually. So where problems involving more than one independent variable, as x1, x2, x3, x4, x infinity, they come under the case of multiple linear regression. Okay. So again, regression, as I said, you have multiple types. You have polynomial regression and all that stuff. So there are different flavors of it, but the principle essentially remains the same. What remains the same? The principle on the basis of which you are trying to fit some line or a curve to the given data. That's the principle of regression. So almost all of them follow the same concept, but the equations, for example, if you take the case of linear regression, you find that the equation is y is equal to beta naught plus beta 1x plus epsilon is the residue. If you take multilinear regression, you find that the equation is different. If it is two independent variables, you get y is equal to beta naught plus beta 1x1 plus beta 2x2 plus some residual value of epsilon. If it is 3, you get beta 1, beta 2, beta 3. Of course, beta naught is the intercept. If it is 5 independent variables, you get beta 1 to beta 2, beta 5 up to beta 5 plus the beta naught intercept plus the residual value. Like this, the equation form will slightly be different, but otherwise the principle remains the same. That's the concept of regression in brief. So what I'll do now is I'll just briefly take you through a little one more example, after which we'll conclude, and I can take up some questions that you have. So I'll just show you as another small case study. Yeah. So this is a small example of hospital data where somebody tried to plot the data of the body weight and the cost incurred. For example, a person who is 49 kilos of weight, if he goes to a hospital for some ailment, the expenditure incurred on that guy is around 6,60,293 rupees. Okay, and somebody with a body weight of 41 kilos, the expenditure on that guy was 8,09,130 rupees, or whatever number. Okay, so there is data has been plotted for about, I think, 249 people's data has been collected, and then this data is given. Okay, data is simple: the body weight and the cost incurred by the person when he goes to the hospital for some treatment. So this is the data that is given. Okay, now when we plot this data using Excel again, okay, I use this scatter plot plot, and then when I plotted, I got this data, which is also. And when I tried to fit the, first of all, I did a correlation. Okay, correlation. So how did I do correlation? I've taken these two sets of data, the same correlation formula that we learned in the about an hour back. I applied the Correl formula. So I've taken these two data sets, body weight and the cost of the hospital. So first is the B2 to B249, there's 249 records. And then I think 248, 249 records. And that is the one set of data. And the cost of the hospital is the second set of data. And you find the correlation, it is 0.34827. So that's a correlation. So you can find out that the value of the correlation is low, which means that the body weight is not a very good indicator of the cost incurred by the patient to the hospital. Maybe there'll be other factors, but just based on body weight, you cannot say that if somebody is 70 kilos, the cost he will incur is, say, only lakh rupees. It's not a good indicator. The correlation is not good, actually. That's one thing. But coming to the concept of regression again, so I've taken the same data, then I tried to fit the regression line. I got this regression line, which is, you can see from the regression line, I got a data of this. My y is equal to, it's a simple regression that I applied because there is only one independent variable here, which is the body weight. And I got this regression line, y is equal to 1846.7x plus 129426 or whatever. R square value you can see is 0.1213. Now, you here in this example, you can see I've used both the concepts of correlation and regression. Correlation, I try to find out what is the relationship, what is the strength of the relationship between the body weight and the cost incurred by the patient in the hospital. That's one thing. And once I found the correlation, I wanted to find out, can we establish a relationship between the body weight and the cost incurred by the patient in the hospital? So when I tried to draw the regression line by plotting this data, I got this equation y is equal to 1846.7x plus whatever number. And based on this, what does it tell you? That X value is the body weight. Suppose I want to find out the cost incurred by a patient who is, say, 100 kilos when he goes to the hospital. How do you find out? You just have to multiply 1846 is equal to 1846, that number, multiplied by 100, plus the intercept value, which is 129,426. You get the value. So I can say that for a person who's 100 kilos in weight, the cost incurred by that guy will be around 3,14,000 or whatever. That's the value that I got from, I think I entered one number wrong, 129,426. Okay. So I got this number so I got a number of 3.4 or whatever. So based on the regression, I'll be able to predict for a different weight or whatever, independent variable, how much will be the value of the dependent variable by plugging these numbers in the equation. I got the number like this. Now, next thing is,
what does R square tell you? R square, as I said, R square indicates the strength of the relationship. This not the strength, the how much the equation is able to explain the data. Here you find that the R square value is very, very low. It is 0.12. So as we have seen in the previous slides, we found that if the line passes all the points, R square value is equal to 1. If the line is passing through, if the points are a little farther apart, then the R square value is around 0.7, and the points become farther and farther and farther. The R square value keeps on reducing. Okay, so here is a case where the points are scattered around, the residues are very high. So if the residues are high, you can recollect from that formula 1 minus RSS by TSS. R square values residue is more, RSS value is more, which means that 1 minus RSS by TSS is becomes very less. So this is a case where the data is scattered around, and the line is not able to fit the data properly. That's why you got a very, very low value of R square, which means that this, you can conclude now, not only from the correlation, but you can also tell the hospital that, body weight is not a good indicator of the cost incurred by a patient. So that's the conclusion that you can draw from the data. You might have to look for other things which can influence the cost to the hospital, but not the value of the body weight of a person. So that's one of the conclusions you can draw from this data. So if you have multiple regression, as I said, you can have multiple variables. So how now to link up all these concepts together, you can ask me, what is the linkage between correlation and these regressions? First of all, as I said in the same example, I showed you how correlation is, you're able to establish the strength of the relationship, and then in regression, I'm able to establish an equation which is able to give the relationship. Okay, that's the second thing. But coming to multiple linear regression, where you can have multiple independent variables, you can have body weight is one variable. There can be, for example, the patient's type of ailment. Suppose he's suffering from one type of disease, the cost might be different. Another type of disease, the cost might be different. Age can be one factor which can influence the cost of the hospital, the cost incurred by the patient. So there can be n number of variables which can influence the cost incurred by the patient. Now, once you establish the correlation, you will be able to figure out, yes, you can rule out certain variables. For example, will the person's height have an influence on the cost incurred by the patient? It may not. The correlation might be very low. Okay, and similarly, the person's age might definitely be a factor influencing the cost to the hospital. Like this, when you have multiple independent variables, your correlation will actually give an indication of what can be the variables that need to be considered and what can be eliminated. Okay, for example, gender, it can be to some extent. A person's complexion, fair colored complexion or a dark colored complexion, will it have an influence on the cost incurred? It may not. It may not. Like this, when you find out the correlations between the variables and then decide what can influence the independent variable and what cannot influence the independent variable, you can decide and then apply the respective equations. It can be linear, simple linear regression or a multiple linear regression. Even in the case of a multiple linear regression, what variables to consider is a big decision. As I said, in some cases, you might encounter even 200 variables or 300 variables. If you end up taking up every variable, then you incur a lot of computation. Many of them will not have influence on the independent variable, which means that you might get wrong interpretation. So these sort of analysis is going to help you a lot in deciding the mathematical, the machine learning models that you actually develop. So that is the implications of learning concepts like this. Okay. So I want to stop here because I have another call at 1 p.m. But if you have any questions, I can take them for the next 10 minutes. Yeah.
Okay, sir. You can stop. We will invite any questions from the participants.
Yeah.
Okay. All the participants, please, if you have any doubts or if you want to ask any questions, please unmute yourself and ask the questions, or otherwise you can post in the chat box. Sir will see and he will clarify the doubts. Please.
Yeah.
Good afternoon, sir.
Yeah, bless ma'am. Yes, ma'am. I can hear you.
Sir, if you have any graph for multiple linear regression equation, I would like to see it, please.
No, as I said, I'll show you. Yeah, I think I showed you that. See, in the case of, can you see my screen now?
Yes, sir. Yes.
So see, if you ask me what is a graph, what happens is when you have more than two independent variables, it becomes like a sheet of paper, like a plane. Okay. So as I said, you can only see up to 3 dimensions. Our human eye can only see 3 dimensions. If it is more than that, we cannot see. So at the most, you can plot 2 independent variables and 1 dependent variable, not more than that.
Okay, sir. Thank you.
Yeah.
So, sir, there won't be any regression line for multiple?
Oh, this is a plane, no? The one you see on the graph. It becomes a plane. It is not a line. It becomes a plane because you have more than one independent variable. Yeah.
Okay. Okay,
Yeah.
sir. Okay.
I think, okay, sir. Thank you very much for the long session. You covered almost all the things related to correlation, regression analysis, the different type of the variables, and all the things. So I think even the layman also understand. Since it is a basic statistics, you will cover all the basic things. So I think it is very useful for the analysis, for the research methodology also. So you given the foundation for the for the basic learners. I think thank you very much, sir, from all the behalf of all the participants and behalf of the Bijar Government Degree College Faculty of the Social Science. I'm very thankful you, sir, to be as a part of our program today from the long session from 10 to almost it is 1 p.m. now. Okay, once again, I'm very thankful, sir. So I think thank you all the participants, and also thank Geeta Sri madam who introduced our speaker today, and the remaining the participants. Today also we'll have feedback and we have quiz on the same class. And tomorrow we are going to cover the basic index numbers and time series by Dr. Venugopal. Please be at 10 a.m. exactly. Okay, so thank you all the participants. Thank you, Srinivas sir.
Thank you, sir.
Okay, thank you very much, sir. Thank you, sir. Thank you.
Thank you.
मतलब बिजली कताज करवाऊंगी शाम को यार इन्वर्टर और आवे तो बिल्कुल टेम आवे